From writing poems to creating full-fledged applications, today's AI almost feels magical. But underneath that magic lies pure math, data, and engineering genius. Every answer you get from popular AI tools like ChatGPT, Gemini, or Llama, it's powered by a large language model. And today, we are taking you inside its brain to understand how it really works. Hi, I'm Huzefa, and welcome to Star Agile's YouTube channel. In today's deep dive into LLMs, we'll explore how AI turns your words into numbers and back into meaningful responses. Next, we'll explore the hidden power of embeddings, attention, and transformer blocks. And at last, we'll see how LLMs are trained, generate language, and create real-world applications. So stick around till the end, and we'll explore AI from inside out, transforming what once felt like a mystery into mastery you can apply. So let's get started. So let's begin by understanding how a large language model actually works. We'll do a deep dive here to understand the basics of this particular modeling technique. So we'll understand what a large language model actually is. Large language models, or LLMs for short, they are a special type of AI which are trained on predicting the next word of a particular sequence. Right? So imagine that as a human being, whenever we write or basically speak, the next word that we output is always dependent on what we have previously spoken. So take this sentence for example. If a large language model is to write this sentence, it will take the previous context into account. So it will see, okay, the first word that it generated was neural, then network, then for, and then depending on this context, it is going to output the next word which is perfectly going to fit that context, which is language. That is how a large language model outputs text, right? So it is designed to predict the next word of a sequence. And all the popular large language models out there like GPT, Llama, Gemini, all of these work on a similar concept. The underlying building block of how a large language model operates, it's known as a transformer architecture. We'll dive deeper into transformer blocks in detail in the later part of this video. Till then, we'll first understand the basics. The first part here is to understand why do we call these models large, right? So why are these models called as large language models? Because the parameters of these models are in billions or even trillions in today's day and age. Take a very popular model, for example, like GPT-3. This model was open sourced by OpenAI long back after it has released more powerful versions of this. But GPT-3 in itself is a huge model. This particular model we are talking about has 175 billion parameters. That's a billion with a B. That's the number of internal parameters which it uses in order to generate the output that you are seeing. And the amount of data which it has been trained on, that the size of the data which is basically it has been trained is around 570 billion tokens. Now just to give you a context around how big of a data we are talking about here, a normal PDF, a normal book that you download from any website, the size of that book ranges around 1 MB. And 570 billion roughly accounts to over 570,000 such books that you are actually training your model on. Right? That's roughly the size or the amount of data which would be present in a large library. So that's the amount of data which has been fed to this model, which gives it the power to predict the next word accurately. To give you another context, if you compress the entire Wikipedia as of 2024, if you take all the Wikipedia articles and compress it together, the combined size of the entire Wikipedia ranges around 100 GB. And that's even lesser than the amount of data which this particular model has been trained on. So the knowledge which has been fed to this model is huge, which actually gives it the power to give such accurate and human-like responses. And this gives the ability for the large language models to be applied in a variety of different fields. Right? So nowadays people are using large language models to build a host of different applications ranging from chatbots, which basically give people the ability to interact like they are interacting with any customer support agent. So nowadays, whenever you log into any website like Amazon, Zomato, Swiggy, So instead of redirecting your chats to a physical person, chatbots first interact with you to understand what your concerns are. If a chatbot is unable to give you your resolution, then the queries are directed to a particular human being at the backend. But the first interaction always happens with an AI agent. The next very popular way of using large language models is in the field of summarization. Because summarization is nothing but you take a huge article. Let's say, for example, you want to build an application that can summarize news articles within, let's say, 100, 200 words. So for that, you basically can train a large language model to take all the data from an article, read it and compress it such that all the information from that article is as preserved as possible. You can even build search assistants. So if you have heard about a tool called Perplexity, which is basically a web browser that leverages AI to summarize the content across multiple different web pages before giving you your result. That's essentially one way of using AI wherein you build search assistants that can leverage the power of AI to give you more human-like responses. And lastly, it is also aiding a lot of developers in writing more accurate code faster. Before introduction of AI into field of coding, each and every block of code was written by human beings, which often took a lot of time to debug, test and deploy. With introduction of AI, the experimentations and the iterations over different pieces of code has become much faster, right? So the sprint cycles that previously used to take 2 months, 3 months to complete, that can actually be completed within a span of weeks now. So that's essentially the power with which AIs can help you out in order to boost the productivity of your applications as well. So we'll first begin by understanding the entire roadmap of this video. The first step before converting or generating any particular response from a human readable text is the step of tokenization. We'll understand how tokenization works, how it converts text into numbers. After that, we'll dive into the concept of embeddings, which takes those tokens and generates vectors which these large language models actually use to understand and predict the next word in the sequence. We'll dive into the details of transformer block next, in which we'll understand how transformers use the concept of attention to pick a particular output accurately. So instead of just randomly guessing which should be the next word to predict, it is going to use the concept of attention to look exactly which part of the previous output is required to generate the next token accurately. We'll dive into the details of attention in just a minute. Then we'll understand how training happens for these language models, because a lot of these open source models out there might not fit your use case. And then you might require these models to be trained on your domain specific data sets. So we'll understand how you can train your own large language models. Once the training is done, we'll understand how large language model outputs can be decoded into human readable text. Right? Decoding is a crucial step because it allows you to take the output from the language models and generate human readable responses from it. Finally, we'll understand a very popular technique of interacting with large language models, which is prompting and fine-tuning. With prompting, you can generate more accurate generic responses. And with fine-tuning, instead of training your models from scratch, you can just change the final layer parameters slightly to fit your domain much better. We'll dive into these topics in detail in the later part of this video. Towards the end, we'll dive into some of the limitations of these language models as well, and how you as a developer can overcome these limitations. And last, we'll talk about the concept of APIs. How other model providers out there have already given you access to their powerful language models, which you can directly use to interact with and integrate within your applications as well. So instead of hosting these language models locally, you can go to these third-party providers like OpenAI, Google, Vertex, Anthropic, and so on, right? And you can use their APIs to actually interact with the large language models which they have themselves trained on this massive amounts of data. So let's begin by talking about tokenization first. Tokenization allows us to convert text into numbers. Why is this required? Because these large language models are trained on numbers. The parameters that we spoken about, those parameters basically operate with numbers. They cannot directly understand text. You have to convert those texts into numbers which it can actually use for doing the mathematical calculations internally. So how tokenization works? Let's understand that. And the first building block of tokenization is to understand the concept of vocabulary. Vocabulary, it's like a dictionary. This dictionary is created by a large language model to keep a track of all the words that it can recognize. So dictionary is basically, this vocabulary is nothing but a set of all the words or tokens, right? So the technical term for this is tokens. These are all the tokens which are recognized by the large language model. Right? So these are all the tokens that are recognized by a large language model. And from model to model, this vocabulary will change. Right? So it's not going to remain consistent all across. It all depends on what technique of tokenization is getting used, which will determine how much of a vocabulary is going to be created by that language model. So what exactly is present in a vocabulary? A vocabulary is going to contain a mapping. Right? So imagine if a particular model has a vocabulary of 10,000 words. So what it essentially means is that it has identified or it can recognize 10,000 words out of all the training data which is available for it. Right? So using that training data, it has identified 10,000 words which can easily be used for generation as well. And these 10,000 words will be stored as a mapping. So there will be a word which will be stored at index 0. Let's say it is A. Then index 1 it stored AA, for index 2 it stored the, for index 3 it stored U, right? So basically each and every word which it has identified will be mapped to a position. That position is going to be an integer. So over here you have 10,000 words. So in all these positions will range from 0 to 9,999. So in a way there will be a mapping created between a token and its corresponding token ID. So right, so this is basically my token which is getting recognized, and this right here is my token ID. This token ID is basically the first way of converting your tokens into numbers. And why do we need to tokenize? I have already mentioned this, because any large language model is incomplete without numbers. So you need numbers, not text, to train or infer from a language model. Right? So this is what gives language models the ability to process language. So if you take an example like a sentence which is I love pizza. So you cannot directly feed this sentence to a model. What you first need to do is you first need to tokenize it or convert it into its individual tokens. So here we'll first say this entire sentence comprises of these individual tokens. The first token is I, the second token is love, the third token is pizza, and the last token is an exclamation mark. So when a sentence gets tokenized, it can be divided into words, subwords, and even punctuations. And each one of this individual entity is present in the vocabulary which we have defined above. So once we have tokenized our words, then we need to map those respective tokens to their token IDs. So from the vocabulary, the word I will get mapped to its respective token ID. The word love will be mapped to its respective token ID. The word pizza will be mapped to its respective token ID, and the exclamation mark will also be mapped to its respective token ID. And that is what tokenization essentially does. It divides your sentence into tokens and then maps your tokens into their corresponding token IDs from your vocabulary. And vocabulary is the entire dictionary which contains mappings between all the tokens and the corresponding token IDs for those tokens. I hope this has given you a broader picture of what tokenization essentially means. And there are multiple different techniques of implementing tokenization as well. There is no single way of tokenization. There are different techniques which are present, but the three most popular ones are byte pair encoding, word piece tokenization, and sentence piece tokenization. We'll understand each one of them one by one. Let's first begin by talking about byte pair encoding. So byte pair encoding is a tokenization technique in which the entire sentence will be first broken down into characters, right? So let's take an example. Let's imagine that there was a particular token called unhappiness. There's a word called unhappiness and you want to tokenize it. So what it will do, it will first break it down into its individual characters, which are U, N, H, A, P-I-N-E-S-N-S. So these are the individual characters of that entire sentence or that entire word. And then it is going to merge frequently occurring or characters together. So what it does, it basically checks which pair of these words are frequently occurring. And all the frequently occurring characters will be merged together until it has done it for all the available characters of that entire set of characters which are present in your input text. So the output from a byte pair encoding will look something like this, wherein you give an input and it's going to merge it in a way such that the most frequently occurring characters are put together. That is what byte pair encoding does. The second way of encoding is called word piece tokenization, which works similar to how byte pair encoding works. But the slight difference there is that when it is merging those characters, it doesn't use frequency, but rather uses probability, which checks how probable are these two tokens or these two characters in occurring alongside each other. So it is going to look at all the available data which it has been trained on and see and identify what's the probability of the first two words. It is going to look at all the available vocabulary and identify what's the probability that these two characters are coming together in that entire information set which has available. And similarly, it will continue doing it, right? So it will identify that U and N are the more probable ones, but U, N and H are not that probable. So it is going to combine U and N together. Then it starts with the next available, which is H. It says H and A occur together, H, A and P also occur together, H, A, double P also occurs together. And same way it's going to create this entire word by itself in a way that basically outputs the sub-words which are most frequently or not frequently, most likely to occur together. Because frequency is used in byte pair encoding and likelihood is used in word piece tokenization. So I'm not using those two words interchangeably. And the last one is sentence piece tokenization, which is the most easiest one, but most language agnostic as well. So the previous two techniques are more tuned towards English characters, right? So it's basically used wherever English is involved. But if you have built a model which is not trained on English data, it is trained on some other language, then how do you tokenize? Because the vocabulary of English is not going to be the same as vocabulary of French or German or any other language out there. So in such cases, you might also need to use encoding techniques which are language agnostic, which is basically the sentence piece tokenization technique. So in sentence piece tokenization, the tokenization basically happens at a character level itself. So a sentence piece tokenization will basically divide your entire text into individual characters and then just use those individual characters at the time of processing. And all the popular models out there will use one of these techniques for generating text. So byte pair encoding is used for GPT models. So models like GPT-2, GPT-3, those models use byte pair encoding. Word piece tokenization is used for training models like BERT, and sentence piece tokenization are used for training models like T5, which are basically most language agnostic models out there. So these are the popular three tokenization techniques. Now we are going to do a quick demo of these techniques in Python and understand how to implement it yourself. So for the purpose of this demonstration, we are going to be using Jupyter notebooks, but you can use any other IDE that you are comfortable using. Right. I have already created a virtual environment that contains all the necessary packages for the purpose of this demonstration. So whatever imports you see here, you might need to install them before you can start practicing alongside us. So let's start by importing our necessary libraries for this demonstration. So we are going to be using a popular library called transformers from Hugging Face. So that's what we are going to be using here. And now we are going to first import the classes that will allow us to demonstrate. So here we are going to use auto tokenizer. So this class of auto tokenizer basically allows us to quickly load a tokenizer based on a given model name, right? So what type of tokenizer we need, I'll show you the syntax on how to load a particular tokenizer here. So let's create a tokenizer based on a GPT model. So here we'll say tokenizer, let's create a variable called tokenizer, and I'm going to use the class auto tokenizer here. The function that we have to use is called from pre-trained. And then you need to pass the model that you need to load, right? So over here we are going to use a smaller model called GPT-2, but you can use any other open source model which are present in the library of Auto Tokenizer. You can go through that entire list of models which are available, made available by them. As I mentioned, this particular model uses the tokenization technique known as byte pair encoding. So I'll also demonstrate that simultaneously here. So first let's create this tokenizer. Once this tokenizer has been created, let's check the vocabulary size of this. So first thing that I'm going to do is I'm going to print what's the vocabulary size of this tokenizer. So as you can see, this particular model called GPT-2 has a total of 50,257 tokens which it can recognize. Right? That's the vocabulary size. That's the number of tokens which it has identified for its entire dictionary for its creation. Second, let's identify what's the maximum length or the maximum number of characters that it can generate. Right? So all these are embedded inside the tokenizer class itself. Right, so this model max length parameter, this is going to tell you what is the maximum length or the maximum number of tokens which this model can generate in one stretch. So 1024 means that once you take this particular model for generation or summarization, it's going to output 1024 tokens for your particular responses. Right, so it can output at max 1024 tokens for your model responses. And lastly, before diving into the details around how this particular model, how the tokenization and all works, the third thing that I want to cover are the special tokens which are recognized by these models, right? So here we are going to look at the spatial tokens map, which contains three kind of special tokens which are generally used by all the large language models. The first special token is called BOS token. BOS stands for beginning of a sentence. So whenever a particular sentence is broken down into a particular list of tokens, you not only need the tokens, but you also need the context around when a particular sentence is ending, when the next sentence is starting, right? When the entire text ends, and if a particular text contains some unknown tokens, how to identify them. So these set of special tokens are doing those jobs for you. So the first token, which is a BOS token, is used at the beginning of a sentence. Right? So if a sentence is beginning, then this BOS token will be used to mark that a sentence has begun at this point of time. EOS stands for end of a sentence, which is used to demarcate that end of a particular text has happened at this point. An unknown token or UNK token is a token which is used for telling that, okay, this is basically a token which is not present in your vocabulary, because this model can only identify 50,257 tokens. It's very much likely that there could be some unknown tokens that you do not know yet. So therefore, in such cases, instead of throwing errors, at the time of tokenization, the tokenizer will map that to an unknown token itself. Right? So these special token maps will vary from model to model. For GPT-2, this is basically the mapping which is used. So for BOS token, so right now you will see that in case of GPT-2, it's a simpler model. So it uses the same set of characters to map basically end of text. So this word right here is the token that is getting used by this to demarcate beginning, ending and unknown token. So all of these are using the same token structure. But this is present for all the language models to mark beginning, ending and unknown tokens from its vocabulary. So now let's dive into how tokenization actually works. So to demonstrate this, let's take a simple sentence that we have written previously. Let's take a sentence which is, I love to eat pizza. Right? So let's say this is a sentence that I wish to tokenize. So how can I tokenize this sentence? I'll basically use the tokenizer .tokenize, and then I will pass the sentence that is supposed to be tokenized here. So when I call the tokenize function, the output of this tokenize function will be the list of tokens that are generated. And let's print these tokens to see each of these tokens individually. So you can clearly see that what it has done, it basically has broken these entire text into individual tokens. I love to eat pizza and an exclamation mark. But one thing that you will note here is that in order to keep track of basically that where a particular word is the first word and when a word is in middle of a sentence, it has added a special character here at the beginning of each token. So here, this particular character that you see, an accented G, this is basically a special character which is appended to a particular text if it is present in between a sentence. Right? Again, this is going to vary from model to model, but generally this technique allows your model to understand that the current token which it is looking at, it's not present anywhere randomly, but it's present inside a middle of a sentence. Same goes with to, same goes with eat, same goes with pizza as well. And the exclamation mark is the last token here, so there is no special character around it. But you will notice that this is the structure which it is going to follow every time a token is present in between a sentence. And once you have generated these tokens, the next part is to understand how to convert these tokens into their respective token IDs. As I mentioned, these token IDs are essentially the integer points wherein in the vocabulary where exactly that token is present. So again, we are going to use the tokenizer itself for converting these. And here the function that we have to use is encode, and we are going to pass our sentence to encode our sentence to their corresponding tokens. So let's run this, and now let's also print the token IDs for these tokens that we have created above. And you will see immediately that I has a token ID of 40, the love here has a token ID of 1842, 2 gets a token ID of 284, eat gets a token ID of this, pizza gets a token ID of this, and an exclamation gets a token ID of this. Right? So that's the first part of converting text into their corresponding token IDs. So next up, we are going to talk about the different types of tokenization techniques and how they differ from each other. Remember, we have discussed 3 techniques: byte pair encoding, word piece tokenization, and sentence tokenization. So let's talk about each one of them one by one. Right? So to demonstrate each one of them, I'll again start from scratch. Right? So again, use the transformers package itself to demonstrate the first technique. Let's import from transformers. We are going to import, let's use the tokenizer for GPT-2 specifically, which is the GPT-2 tokenizer. Right? For demonstrating the tokenization technique used in BERT, which is the word piece tokenization, I'm going to use BERT tokenizer. And lastly, to demonstrate how the last particular tokenization technique, which is used for T5 models and on, I'm going to import auto tokenizer because that allows me to load the T5 model as well. So I've imported all these 3 classes. So we'll use the individual class to demonstrate the tokenization technique one by one. We'll start with the GPT-2 tokenizer itself. So let's create a tokenizer for that. So here we'll say tokenizer underscore byte pair encoding, because that's the tokenization technique which is involved here. Right? So here you can create a class from GPT-2 itself. Right? And that will be the BERT byte pair encoding tokenizer. And then you can demonstrate different techniques. Right? So let's try to encode each sentence one by one. So here we'll say tokenizer underscore BPE dot tokenize. Let's take a word that we have demonstrated. Let's take a word called unhappiness. Right? And see how the output looks like. So you will notice that in case of this particular word, what it does is essentially it has divided this entire word into 3 individual tokens. So UN is the first pair which has identified that it's the most frequently occurring pair. Then the second is H, and the last is APPINESS or happiness. So as per its vocabulary, right, these are the set of tokens that are most frequently occurring together, and that's why these are the tokens that are outputted for the word unhappiness. Let's take a more complicated example, right? So let's take now machine learning, for example. So here we'll replace unhappiness with machine learning to understand how these 2 set of words are going to be tokenized. So when I run it, you will see that here the outputs contain machine and learning. Now why these 2? Because now machine and learning, although learning is a token in itself, but since this is basically a part of another word, you will see that at the beginning here that special token that we seen previously, right, this gets appended to it. Right? So this indicates that learning in this context is part of a larger text, right, and it's a word in itself, right? So it is present at a word boundary, and therefore you see a special character has been appended in front of it. So that's basically the first tokenization that I mentioned, which is a byte pair encoding, which takes the characters and continues to merge it based on their frequency of occurrence. The second tokenization technique is known as word piece tokenization. So let's create a tokenizer for that. In this case, we are going to use the BERT tokenizer, right? And we are going to use a model called BERT base uncased. So this model is basically a BERT model, a base BERT model, meaning that this is the simplest of the BERT model, and uncased means that it doesn't differ between uppercase and lowercase, right? So it contains the text in a entirely uncased manner. And let's create a tokenizer here, and we'll take the similar sentences that we have created above to see how differently the word piece tokenization is going to, operate on these. So here we'll say tokenizer dot tokenize unhappiness, and immediately you will notice the difference between the first and the second one. So here it has identified UN as the most probable pair. So here you can see UN is at least present, but the previous tokenization has only tokenized H, but here it has tokenized HA together, and in front of it, it has put two hash symbols. Now, the previous case I have mentioned that each and every model has its own way of identifying when a particular token is a part of a word or when it's a part of a sentence. So in such case, you can see that unhappiness is a complete word in itself and HA is a subword from it. So in order to make sure that it is known to the model, here it has put two hyphens. It has put two hashtags in front of it. So both of these hashtags put together means that this particular word HA is a part of a bigger word, and it continues here as well and the last word as well. But you can see clearly, right? So each tokenization technique will work differently. If you take the second example of machine learning, there also you will see the output will be slightly different. So let's tokenize that as well. Right? So in this particular case, you will see although the words are same, but this tokenization technique does not mark a special character in front to denote that the word itself is a part of a larger sentence. It only demarks it when that word has been broken down into subwords. So when you have a bigger word which is broken down into subwords, then only it's going to put special characters in front of it to demarcate that particular thing. So that's the second tokenization technique, which is word piece tokenization. The third tokenization technique, which is basically called as sentence piece tokenization, is used for training models like T5, right? So that is what we are going to demonstrate here as well. So let's create a tokenizer. This is the sentence piece tokenizer, and we are going to use the auto tokenizer for this from pre-trained. And this time the model that we are going to use is from Google. So here we are going to use the BY T5 small model. So this tokenization is again, it's basically using a T5 model only. So this T5 model is a type of a large language model which is basically trained to be language agnostic. I'll not go into details around what exactly happens with T5 right now, but this is a type of a large language model which is developed by Google. And now this tokenization, we'll use the same tokenization again. Here we'll see how differently does it tokenize unhappiness and machine learning. So as I mentioned previously, with sentence piece tokenization, the entire word is broken down into its individual character, and each character is basically a token in itself, right? So in this way, the model does not have to look at how those tokens are interacting with one another. It's going to break that entire text into individual tokens, and it doesn't matter which language it is from, right? French, English more or less have the same set of characters. So when your tokenization is at a character level, you don't need to basically think about what those tokens are put together to create words. So when the model gets trained, depending on the context of the nearby characters, the model will try to predict the next character for the output, right? And same way, when you do it for machine learning, you are going to see a similar response. So here as well, each and every token is basically a character of that entire sentence of machine learning, right? So you can see even a token has been created for white space, right? And that's basically the differences between these three popular tokenization techniques. So next up, we have to understand now the concept of embeddings, because tokenization basically converts our words into their token IDs. But those token IDs are nothing but individual integers. How will they communicate their meaning to the model, right? So embeddings are essentially a set of vectors which incorporate the entire meaning of that particular text that you are trying to feed to your model. So in simple words, in order to understand embeddings, let's take a simple example. Imagine you are trying to process words like king, queen, man, and women. Right? So let's say these are the 4 words that you are trying to encode or embed. So what model will do, the first step of this particular process would be to basically convert each of these words into their respective token IDs, right? So let's say these are mapped to their respective token IDs. Right? So whatever these token IDs are. But then we also require some understanding of what king stands for, right? So, and what queen stands for, what man stands for, and what women stands for. As a human being, you know how to use these words into sentences, right? But for a model, it needs to be learned. So model needs to learn when to use man, when to use women, when to use king, and when to use queen. So contextually speaking, when you convert these words into their respective vectors, right? So internally, there is a matrix which contains the vector embeddings for each of these token IDs, right? So we know now that each and every word is stored as a token, but there is also a matrix that is created which stores the embeddings for each and every token, right? So along the rows, if you imagine that you have these different token IDs, and along the columns there will be a vector which will be stored for corresponding embedding of that token. How big of this vector it is, it depends again from model to model. Some models have smaller vector sizes, other models have huge vector sizes, right? The larger models have even bigger vector sizes, right? So these embeddings, these vectors are essentially created to incorporate the entire meaning of that word. And when you use these words, or so when you use these vectors, you can actually perform mathematical operations using it. What do I mean by it? So imagine you take the vector of the word king and subtract from it the vector of the word queen. So the resulting vector that you are going to get, that resulting vector will be very much parallel to the vector that you are going to get by subtracting the vector of man from the vector of women, right? So because these words are basically encoded into their vectors, when you do simple mathematical operations using vectors like subtraction or addition, the resultant vectors that you get from these two pairs are also going to be parallel. And not only this, if you take another example, let's take words like India, Delhi, USA, and Washington. So we know that India is a country, USA is a country, and Delhi is the capital of India, Washington is the capital of USA. So when you take the vectors of these 4 words and do similar operation here, that you take the vector of India, subtract the vector of Delhi from it, you take the vector of the word USA and subtract the vector of the word Washington from it, the related vectors, the resultant vectors that are generated, those vectors will be parallel to each other, right? So in other words, similar meanings will be encoded within similar vectors, right? So because of that fact, you will find the vector operations are valid for the embedding vectors that are generated here. And this gives vectors a whole lot of importance. So where can actually be used? So these vectors can be used to measure similarity between words, right? So if I give you 2 sentences, or if I give you 2 words and I ask you to tell me how similar they are, why this might be used? Imagine that you have a chatbot and you want to implement a very simple way of giving solutions to user queries. So user can come in and they can ask a question around delivery time, and you have some structured responses that you have available based on what you need to output. So you have a user query and you want to see what is the most similar response that you can give in order to get the right answer. So you can actually run a similarity search of your user query, convert that query into the vector embedding, and scan through all the responses available to give the most accurate response from your list of available responses. So that is basically a very important implementation of embeddings, because they allow you to perform a similarity search. Then you can even perform semantic searching. Semantic searching is basically nothing but when you want to perform a search based on the meaning of a sentence. So the example that I just gave, it falls more in the domain of semantic search, but it also uses the concept of similarity, so that's why I gave in between the two. But semantic searching is basically when you take a larger text, not just a word, but you take a sentence and you encode the entire meaning of the sentence in a same dimensionality vector, right? So let's say I give you a sentence, I love pizza. In that sentence, there are 4 tokens or at least 3 tokens, I, love and pizza, and each token will have its own embedding. So how do you basically compress that information into a single vector that incorporates all the semantic meaning of it? So that is basically done by multiple pooling techniques. We can talk about it later. But the key part of a semantic search is to essentially encode all the information which is present inside a text into a same dimensionality vector and then search through to get the most semantically similar answer. And also these vector embeddings are used in RAGs. So in one of our previous Star Agile videos, we have already deep dived into what RAG is. So in RAG, you basically take your source document. Using semantic searching, you basically encode it into vectors and store it into a database. And whenever new input comes, you run a semantic search and identify the most similar values from those documents and return it back. So RAG stands for Retrieval Augmented Generation. It's one of the techniques which is used for improving the outputs from large language models. And embeddings are also used for embedding documents within RAG databases. But yeah, these are the various opportunities that you get for using embeddings in the domain of AI and machine learning. In this demo here, we are also going to see how you can visualize embeddings as well. Because imagine you have an embedding vector of 300 dimensions. As a human being, you can only visualize things in 3 dimensions, not more than that. So how do you actually take a 300 dimensional vector and visualize in a 2-dimensional space or a 3-dimensional space? We are going to use a technique known as principal component analysis, or PCA for short, which is going to take this 300 dimensional vector or more and compress it down to just a 2-dimensional vector. This compression algorithm is very much popular in the domain of machine learning, which allows you to compress the data from a higher dimensionality into a lower dimensionality by compressing as much as information as possible. So to understand how PCA will work, just take an example from your day-to-day life. So if you have an image which is of 100 or 200 megabytes and you want to upload it to a website, so typically the websites might not support uploading documents more than 1 MB or 2 MB. So what do? You basically go to, you take use of tools that can actually compress the details present in those images. And that compression is basically what PCA can also do. So in PCA, you take a bigger dimensionality vector and you compress it into a lower dimensionality by preserving as much of information as possible, right? So that is what PCA will do. So, and in this demo, we are going to see how using PCA you can actually visualize a higher dimensionality vector into a lower dimensionality as well. So let's get into the hands-on demo and see embeddings in action. Alright, so now let's see how you can create embeddings and visualize them easily. And we are going to do, and I'm going to show you 2 different ways of creating or generating embeddings, right? So first we will use GPT-2 only to create embeddings for a particular text and see how we can actually use sentence transformers to create semantic embeddings as well. Let's start off by implementing or importing our necessary libraries. So we'll first import Torch, which is basically the PyTorch library that we are going to use. Then we are going to import some classes from Transformers library, so from Transformers package as well. So I'm going to import GPT-2 model and GPT-2 tokenizer as well. I'm going to import NumPy. Going to use NumPy as NP. And lastly, I'm going to import from scikit-learn dot matrix dot pairwise import cosine similarity. So this function of cosine similarity is basically the one that we will use to validate whether or not two vectors are similar or not, right? So this cosine similarity is again a very popular concept from the domain of machine learning that allows you the ability to measure the similarity between two vectors of same dimensionality. So we'll use cosine similarity to measure distance between two vectors here. So let's start by creating our model in our tokenizer first. So here we are going to create the model using the GPT-2 model itself. And then the tokenizer that we are creating here, again this is the GPT-2 tokenizer. We are going to use it to be created from .pretrain GPT-2 model only. Now let's create a couple of sentences that we want to actually validate are similar or not similar. So here let's create a pair of sentences, a few sentences for that matter itself. So let's say the first sentence is I love eating pizza on weekends. That's my first sentence. Let's say the second sentence is my favorite food is pizza. And let's say the last sentence that we want to look at is, let's say I went for a walk in the park yesterday. Alright, so these are the three sentences that I want to use, and the goal here is to basically see how you can create embeddings for each token of this sentence, and you can combine those embeddings to create embeddings for each word as well, right? So we'll see and practice that now. So the first part of this is to basically define a function that can help us generate these embeddings. So let's define our function here. Let's call this function as get GPT-2 embeddings. Right? So this function is going to take a sentence, it's going to take the model and the tokenizer to generate the embeddings for our output. So here the first input to this model will be the sentence that we want to encode. Then we will see the model that we want to use, which I have already defined above, and the tokenizer that is supposed to tokenize this particular sentence. Right? So these are the three inputs to this function. And what I am going to do next, and once we have defined this function, the next step is to first generate or tokenize the sentence into its respective inputs. The first thing I'll do is basically tokenize here. So here using the tokenizer, I'm going to tokenize the input sentence first. And now instead of using the tokenize function that I did previously, over here we are going to directly use the tokenizer class, right? So the constructor itself will be used to generate the inputs required for generating the embeddings. I'll show you what these inputs are first, right? So let me do it outside here so that I can show you how it is different from our previous implementation. So what I will do is I'll basically use the tokenizer class, and so I'll use the tokenizer here which we have defined, and to this tokenizer we are going to pass a sentence. So let's take sentences. Let's take the first sentence from our list of sentences. I'm going to return the output tensors as PyTorch because the output here needs to be processed using PyTorch. So that's why in this particular demonstration I'm going to be returning tensors using PyTorch, right? And in this particular case, let's just keep it at that, right? So I don't need to encode or do anything else here. So let's do these tokenizers, or let's even define padding here. Padding is true and truncation will also be true, and let's set a max length to 512. So what I am doing right now is basically I am using my tokenizer that I have defined above to tokenize a sentence, return the output as PyTorch tensors, right? So here the output will be returned to me as PyTorch tensors. Now remember that I want to generate each token as a maximum length of 512, right? So I want to make sure that the maximum length of the tokenized output is 512, and in that case I also might require padding here, right? So although this is not mandatory, so let's just omit it for now, right? So we are just going to encode a sentence and return the output as PyTorch tensors. right? So I have defined my tokenizer, and once this tokenizer has been defined, let's see what the, no, actually this should not be a tokenizer, 1 second. Let's store it in a different variable, let's call this inputs. So once I have my inputs, let's see what it contains. So you will see that the output of this particular tokenizer call, it's essentially a dictionary that contains my input IDs, which defines basically what the input IDs for my sentence are. So I have already demonstrated what these look like. So these input IDs basically map each token to its corresponding token ID, right? And lastly, we have an attention mask that tells you which of these tokens are basically actually present in the sentence and which are not present in a sentence. Now, a lot of times what you might require is to make sure that the output sentence that you are generating, the tokens that you are generating, is of same length. In that scenarios, you might also require some padding tokens, some extra tokens that make your length of your tokens equal. In such scenarios, the attention mask for those will be 0. That allows your later on models to understand, okay, you do not need to pay attention to those because those are just dummy tokens that are added to the sentence. If no dummy tokens are there, then the attention mask will be 1 all across. But if your output contains some dummy tokens, in that particular case, your attention mask will be 0 in between there, which indicates to the model that you do not need to pay attention to those particular tokens. Right, so over here inside our embeddings, the first step is to essentially tokenize our sentence, and that's what we are going to do here. Right, so I'm going to tokenize my sentence and I'm going to return the output as PyTorch tensors. So here we'll say return tensors as PyTorch. So this is going to convert my input sentence into PyTorch tensors. And then the last thing that we have to do is convert these inputs into our embeddings. So for generating embeddings, obviously we will need our model. Right, so the model is going to be the one that will take my sentence and generate embeddings from it. Okay, so here we are going to generate embeddings using our model itself. So we have already defined our model previously. So I'm just going to generate embeddings, or you can call it outputs as well. Okay, the first thing is basically to process this entire thing with Torch. So after you have generated this embeddings, after you have generated your inputs, the next part is to feed those inputs to your model, so that the model can process it and essentially generate my outputs, right? So first thing I will do is I will essentially pass these inputs to my model to calculate the embeddings for each and every token, because without passing it to the model, you will not be able to calculate your embeddings. So here we'll say with torch.nograd, right? So why am I using torch.nograd here? The reason for using torch.nograd is because without this, if you do not provide nograd, PyTorch will do a forward pass through your language model, and it is also going to conduct a backward pass to calculate the gradients with respect to each parameter. Now if you do not disable gradients, the memory which will be consumed will become exponentially higher. So in order to avoid calculation of gradients for each and every parameter, I am going to set no grad, which indicates to PyTorch that do not calculate gradients during the forward pass. Right, and then what I will do next is basically I will pass the inputs to the model to calculate your outputs first. So here we'll say outputs equals model, and into this model I am going to feed all of my inputs. Right, so here what happens is that now the model will get the inputs that I have created. Now inputs contain the tensor that contains the input IDs, and it also contains the attention mask, which tells the model which tokens are supposed to be looked at and which tokens are supposed to be ignored. Right, so both of these are fed to my model to calculate the outputs, and once I have my outputs, then I can generate the embeddings which are created by the model. Right, so these embeddings are basically outputs dot, you can take it back from the last hidden state here. So what will happen now is that whatever the last output of the model will be, that will tell me the embeddings which are generated for this model. And these embeddings are what encode the meaning behind each and every word. Without embeddings, your model will not be able to understand what the text looks like. So over here, we are taking the embeddings from the final output layer of this model, right? So we haven't discussed transformers yet, but in order to help you visualize, a transformer or a large language model contains multiple layers of blocks. So the final output here we are taking from the last block. So here there are layers of blocks which are added, which are doing the same operation, but on a different set of inputs to get the final output. And we are generating the output from the last hidden state to get our embeddings back, right? And in this particular case, we have our embeddings over here. Now remember, these embeddings that we generate will be generated for each and every token which is given to us, right? So these tokens, each token will be generated or compressed into an embedding. So what I want to do is, first I want to take the embedding for each word, right? And then I want to pool it or combine it together to calculate a sentence level embedding. So in this demonstration, what I will do is, I will take the embeddings of each token, right? So each token embedding will be generated, and the next step is to actually calculate the final embedding by averaging all those individual embeddings, right? So here what I will do now is, I will calculate my sentence embedding by actually using the embeddings generated previously. So here I'll use torch.mean, and I'll calculate the average of my embeddings that I have generated, and I'll say that the dimension across which this average has to be calculated is 1. And then finally I'll return my sentence embedding, right? And let's just compress the data. So we'll use this squeeze function to reduce the dimension. So as you can observe here, we have the token ID, but this is mapped in a batch layer, right? So the shape of this tensor is basically 1 by 7, or what, 1 2 3 4 5 6 7 8, 1 by 8. So we do not need the batch dimension here, we only need the dimension of the embedding. So I'm just going to squeeze it off so that it is not generated in the output, and I'm going to convert it into a NumPy array so that we can visualize it much better, right? So this function is basically going to generate the embeddings for me using the GPT-2 model, right? So with this GPT-2 model, I'm going to feed the sentence. That sentence will be basically broken down into individual tokens. Those tokens will be fed to the model to calculate my embeddings for each and every token, and then I'm going to compress those embeddings to calculate my sentence level embedding by providing the average function there, right? So this function is now ready. The only thing that is left to do is basically now to use this particular function to calculate individual embeddings for each sentence, right? So let's create a vector that is going to hold all the embeddings for me, and then I am going to iterate through each sentence, right? So I am going to iterate through each sentence, and then I am going to calculate the embedding for that particular sentence by calling the get GPT-2 embedding here, and we can even print it out if you want, but instead of just printing it, I am going to append it in my embeddings list, right? And let's print the shape of this embedding, and also let's print the text here. So as you can see in this particular case, the first sentence is basically, I love eating pizza on weekends. So this particular sentence has been compressed into an embedding of 768 dimensions. And you will see that across all the sentences, the first sentence is, I love eating pizza on weekends. The second sentence is, my favorite food is pizza. And the third sentence is, I went for a walk in the park yesterday. And all of these sentences have been compressed into an embedding of 768 dimensionality, right? So all the embeddings here are of the same dimensionality. But the next question, let's print these as well. Let me print my embeddings. And you will see that all of these embeddings basically are a NumPy array which contains some random numbers. Now immediately from the raw naked eye, you won't be able to make any sense out of it. Why? Because these embeddings basically encode some information which you as a human being are not supposed to understand. This is meant for the understanding of the model itself, how the model is going to take this data and actually output the actual results that you want to look at. So the next thing that we are going to do here in this demo is to actually calculate the similarity between these vectors, because embeddings, as I mentioned, are supposed to encode representations into meaningful context. So here what we want to do is, we want to calculate the similarity between these individual embedding vectors. So for that we are going to use a function called cosine similarity. So let's write a simple function loop again. Right, so we have basically 3 sentences itself, or we can just run it for the length of sentences, and then let's create another for j in the range of length of sentences if I is not equal to j. So here what I'm doing is I'm iterating through each sentence and I want to calculate similarity for each pair of sentence which is present in my list of sentences, right? So in this particular case, even I don't need to run this, actually a simpler way of doing it. So I need to iterate through each sentence and then I'll iterate through the second pair of sentences, and I'm going to basically compare the similarity between the pair of sentences here. Okay, so before that, let me do one thing. So first let's calculate the similarity matrix. So let's create a similarity matrix by calling the cosine similarity, and we'll pass the embeddings here to calculate the similarity directly, right? So we already have calculated our embeddings and we have appended it to a list. So I can then pass this list to the function of cosine similarity, which is going to output a matrix that contains similarity between each pair of sentences in my list. So let's print this similarity matrix here. And one thing you will notice here is that we have 3 sentences and each sentence has the highest similarity with itself. So you will see along the diagonal, all the sentences, the similarity is 1 because one sentence will always be similar to the same one, right? So if you take I love eating pizza and you compare that with the same sentence, it is completely similar. So therefore the similarity will be 1, which is the off diagonal entries that we have to focus on. But unfortunately, you will notice a very slight complication with GPT-2. So as I mentioned, this GPT-2 model is trained on predicting the next word in the token, right? It is basically going to take my previous context, but the output for each and every timestamp will be a word in itself, right? But this does not mean that it is able to compress all the semantic information of that whole word. Whatever the sentence contains, it might not be able to preserve that information that well. And that is actually reflected in this output similarity matrix as well. So when you take these sentences, like you take the first sentence here, right, which is I love eating pizza, that was the first sentence. So this first sentence obviously has the highest similarity with itself. But when you take a look at the similarity of the second one, it is also good, which is suppose you expected, because the first sentence is I love eating pizza and the second one is also my favorite food is pizza. So both these sentences are talking in the context of pizza. So they are supposed to have high similarity, but you don't expect a high similarity between sentence 1 and sentence 3. But that is not the case here. So when you take a look at the result, sentence 1 and sentence 3 similarity is also pretty good, right? That actually proves the point that GPT-2 as a model is not going to preserve, or it's not trained to preserve the semantic relationship between text. It can predict the next word accurately, but it will not be able to compress all those information to create a single tensor of your semantic relationship, right? So in that scenario, right, so what is the option here? Because GPT-2, it's not a sentence transformer, right? So this particular model, or this transformer model that we are talking about, it is trained on predicting the next word. But you need, in order to calculate accurate similarities, you need models that can preserve the semantic similarity as well. And to demonstrate which model can do it, we again will take help from a sentence transformer model this time, right? So in this second demo, I am going to show you with the same set of sentences, actually how can you calculate similarity in a much more accurate way. Okay, so this time we are going to make imports from the sentence transformer package. So I am first going to import sentence transformer, plus I am also now going to import PCA, or principal component analysis, which will help me to visualize also how these sentences are located in a 2-dimensional space. So I'll say from scikit-learn dot decomposition import PCA, and I'll also import matplotlib, which will help me to visualize these individual vectors better. So the first part here is to define our model, right? So I'll again use the model, but this time I am going to use the sentence transformer model. And one particular sentence transformer model that we are going to use here is this one, which is all mini LM 6 layers version 2. So you will find the details about this model on the sentence transformer package website as well. The documentation contains all the details about this model. But just to give you a brief, so this particular model has been trained to predict a particular sentence which is most similar to my current sentence. So unlike the previous training analogy, wherein the objective of the training was to predict the next word based on the context, this model has been trained to predict the most similar sentence for the current given sentence, right? So it is actually trained to predict the most similar pair of sentences. And this gives the model the actual power to encode as much semantic relationship as possible of the input sentence. And when we generate sentence level embeddings, there this particular model will give me more actual or more useful embeddings as compared to the last model. So let me define this model first. It can take just a minute to load. Right. And once this is done, then I can actually take all of my previous sentences and it is much easier to encode these, right? So you can also use the sentence transformer model in the same way that we did previously as well by individually encoding each token and all. But in order to avoid that much detail of implementation, the developers of this package have given you just a single invoke function, encode function that you need to call. And to this encode function, you can pass your sentences. And what it will do automatically, it will pass you embeddings for these sentences without you having to manually iterate through each token and embed those tokens and pull it together to calculate the sentence level embedding, right? If you wish to look at those details, again, you can go to the documentation for this particular model. There they have given you the exact detail around how, if you want to, you can actually implement this in this fashion as well, wherein you iterate through the sentence, calculate the tokens, calculate the embeddings of the token, and then pool those embeddings to calculate the sentence level embedding as well. So that also you can implement yourself, but here in order to avoid that much complexity, you can directly call the encode function that is going to give you the embeddings for all the sentences that we have provided here. And now once we have the embeddings, we can again then quickly calculate what the similarity looks like, right? So let's again quickly calculate our similarity matrix. By using cosine similarity and passing our embeddings, and let's print the similarity matrix here. So this time around you will see the similarity actually representing what we wanted to show. Along the diagonal we have the sentences themselves, so the sentence will be most similar to itself, so therefore along the diagonal all the outputs are 1. But if you look closely, the first sentence which we have now is I love eating pizza. This is similar to my favorite food is pizza up to 66%. So these two sentences are having 66% similarity between themselves, right, which is good. And the first and the third sentence are having much lesser similarity, right? So in this particular case, the first two sentences, because they are talking about pizza, the context is more or less same, right? It's not similar, right? So the second sentence talks about what your favorite food is, and the first sentence talks about pizza from the context of you eat it on weekends, right? So the concept, that the objective of that is same, that is the topic of that particular sentence is pizza, but the context in which pizza is getting used is slightly different. So that's why the similarity, although is high, it's not 100% there. And same way the first and the third sentence, both of them are talking about two completely different concepts altogether. So therefore the similarity here is lowest, right? So you can clearly see that it is only 28% similar to the last sentence. And same way if you take a look at the second sentence is again 66% similar to the first one, but it's again very less similar to the last sentence. Again, that is something which we know, because the second sentence here is saying that my favorite food is pizza, and the last sentence here says that I went for a walk in the park yesterday, which is again talking about two entirely different concepts altogether. And over here you can clearly see that in action. So therefore these are not similar at all. And let's take it one step forward and visualize it as well, right? So obviously here 768 dimensional visualization is not possible. So what I'm going to do is I'm going to use PCA to actually compress it down to a lower dimensionality. So first I'm going to use the PCA class to define how many vectors I want to output, right? So what's the dimensionality of the vector that I want to create, right? And then I'm going to actually define this, and then once my PCA has been defined, I'm going to use PCA to actually transform it, or you can just call fit transform, right? And this will basically give me the output embeddings for the resultant vector. So here I'm going to call it embeddings 2D. So this embeddings 2D are essentially the embeddings but compressed down to just 2-dimensional. Now since I have the embeddings in 2-dimensional, I can actually visualize it on X and Y axis. So for visualization I am going to use matplotlib. So over here we are going to quickly create a figure first, which is a matplotlib figure. Let's define a bigger figure size here, and let's I think we can just scatter all the embeddings here by using the scatter function. So here we are going to use the embeddings. So on x-axis I am keeping all the values, like so, because it's a two-dimensional vector, I want to put the x coordinates on the x-axis and the y coordinates on the y-axis. So in this particular case you can basically divide it like this. So all the rows from the first column which indicates the x coordinates, and all the rows from the second column which indicates the y coordinates, and then you can actually create these dimensionalities 1 and 2, so the first dimension and second dimension, and the title of this particular plot will be sentence embeddings. And you will clearly see that these two sentences, this is the first sentence, the second sentence, are closer to each other. Why? Because both of them are actually having the similar concepts. But the last sentence, which is basically the third one, is very much far away from both of these two sentences, because they don't share any similarity with each other, and as a result both of these sentences are not going to be closer to the third sentence which is present there. And that's essentially what embeddings do. They allow you to compress a lot of information into a dimensionality vector that these models use to analyze those meanings behind those words and tokens. So now we are going to understand the inner workings of a transformer block. As I mentioned previously, all these large language models inherently have these multiple repeating transformer blocks that allow these models the ability to generate such brilliant responses. Here we are going to understand the key working mechanism underneath a transformer block, which is the attention mechanism. All these transformer blocks, they inherently work on the same principle of attention, or self-attention to be more accurate. So what exactly is the meaning of the word self-attention? Let's try to build up on that. So self-attention means that in a particular sentence, each word is going to look at all the other words in the same sentence and try to see for that particular word which other word is having the most importance or most relevance. Right? So if you say, I love eating pizza on a weekend, and you want a transformer to basically generate this sentence for you, so each and every time at the training phase, it will look at, okay, if you want to generate this sentence, it will first try to understand for each word which other words in the context are giving it the most relevance. And this particular attention mechanism is the key working principle of all the transformer blocks. It helps these transformers to build rich context. So what does mean? What is the meaning of richer context? So we have already discussed the embeddings of a particular word, but embeddings are essentially described for one essential word, right? So it does not take a broader context into account. So when you train a large language model, it is important to give the context of that sentence to that word as well, because the meaning of the word can very well change in the context around it, right? So if you say, I am using an Apple phone versus I want to drink an apple juice, so the word apple remains the same in both the sentences, but the context around each sentence give that word a different meaning altogether. So in the first sentence, you are talking about the company called Apple which produces phones, whereas in the second sentence, you talk about Apple from the context of fruits. So context becomes very much important, and it is the mechanism of this self-attention which gives LLM power to build a much richer context while generating the next token. So next is, how are these particular attention mechanisms working? So the key working principle of attention are query, key and value vectors. So first let's try to understand what exactly is the meaning behind queries, keys and value. So we are going to indicate query vectors with Q, key vectors with K and the value vectors with V. And what happens, in order to get an intuition around it, consider that each and every word is basically a query vector. So we basically map the embedding of each vector to query, keys and value, wherein query indicates the question that we are supposed to ask. So here the question we are asking is basically try to find the most similar word to my current word. So the query vector is essentially the question that we are finding the most relevance for. Keys are all the other words in the context of the current word. Right? So these are all the possible answers to your questions that are available. So depending upon the most relevant answer, we want to find that particular answer for the query that we are searching for. So what the attention mechanism does, it basically creates, first of all, it does a dot product. So it computes something known as an attention score. So the first thing that it does is basically compute something called as attention scores. So these attention scores are calculated by doing a dot product between the query and the value vectors, not the key vectors, sorry. So in this case, the dot product is done between the queries and the key vectors. So this dot product is basically going to tell it how much attention it needs to pay to a particular word. So the words with higher similarity, right? So the words with a higher similarity, so dot product is nothing but a way to calculate cosine similarity. So whichever pair will have a highest cosine similarity will get the most attention, and whichever has the least cosine similarity will get the least attention. So this particular output will give it a vectors of scores, right? So what is the score between the first pair, what is the score in the second pair, third pair, and so on. And once you generate these scores, what it does next is basically it creates a softmax. It does softmax to make sure that all of these attention score add up to 1. So here we calculate the softmax scores, right? So these softmax scores are calculated, and once you have these softmax scores, or in other words, you have the attention scores, you take the actual value that you are essentially containing forward. So this value is nothing but the context that you take forward, and you richer this context. So remember, the goal is to use attention to create a richer context. So the context is present inside my value vectors. So what I do then is finally I take the softmax scores and essentially apply these softmax scores upon my value vectors to get a much richer context. And that is how attention gives you the power to build a richer context. So here the key thing here to note is the 3 vectors that we use: queries, keys, and values. And each transformer block builds its own set of queries, keys, and value vectors. And it's not only limited to one set of vectors for each transformer block. In each block, you can have hundreds of such parallel query, keys, and value vectors working simultaneously to derive as much possible information as possible. And these multiple sets of queries, keys, and value vectors together are known as attention heads. So in one transformer block, there can be several attention heads that are working parallelly to generate as much information as possible from the underlying embeddings of those tokens. Right? So in the demo here, I am going to show you quickly how this works. So although this diagram is basically a pictorial representation of the same, right? So each query vector is going to look at the keys which are present. So each key vector will correspond to a token. For each token, it will calculate the dot product, calculate the similarity scores, and those similarity scores will be then imposed on the values to make sure the context which is going forward is as rich as possible. Right? So that's in detail how attention mechanism works. Okay, and in case of transformers, these attention blocks are stacked on top of each other to create a deeper understanding of the underlying model. Let's quickly do a visualization and see how this particular mechanism works in real transformer architectures. So, to begin with, we are again going to start by importing the necessary libraries for this demonstration. So for this demo as well, we are going to use transformers package, NumPy, Matplotlib, and Seaborn. So let's start by importing NumPy. We are going to import Matplotlib as well. Let's import Seaborn to visualize the attentions. And then from transformers, let's say we are going to import auto tokenizer and auto model. And I think that's it, right? And let's also import PyTorch, right? So these are the necessary imports that we require. Let's create for this particular demonstration, we are going to be using a BERT based model. So let's create a variable that can contain our model name. So here we are going to use the model BERT base uncased, or instead of BERT, let's use distal BERT because that's even a better model. Right, so this is the model that we are going to use for the purpose of this demonstration. And once we have the model name, let's quickly create a tokenizer based on the model that we have provided. And let's also define our model. So here we are defining a tokenizer and a model using the above, and plus one thing we have to note here is that when creating the model, we need to tell it to output attentions as well, right? So attentions by default are not generated when you are creating the results. But for this particular demonstration, we also need the attention vector. So here we are asking the model to output attentions along with outputting the embeddings and the other entities that it creates. Alright, so now let's create a function that can quickly extract our attention weights for a given sentence. Right, so here, just like the previous demonstration, here also we are going to define a function. Let's call this function as get attention weights. And this particular function is going to take a sentence, a model, a tokenizer, plus you also need to pass, like if you want to, here we are going to pass from which layer and which head we are getting the attentions from. Because as I mentioned, in a typical transformer, there can be hundreds of transformer blocks stacked on top of each other. And within each transformer blocks, there can be hundreds of attention heads that are parallelly working on generating attention scores. Alright, so you need to mention from which layer you want to extract, and within each layer which head you are trying to take a look at. So by default, the default values are layer 0 and head 0, right? So that's the two default values that we are going to use here. Now, once this is done, let's now quickly process the sentence to get the inputs, and then we'll use the inputs to generate the outputs. So here the inputs are nothing but the outputs generated by our tokenizer. So we'll pass the sentence, we'll ask it to return the tensors. So over here we are creating PyTorch tensors. We'll make sure the padding is set to true and truncation also is set to true. Right, so once we have our inputs, we can then pass those inputs to our model to get the outputs. Remember, I have already shown what inputs contains. Input will contain the input token IDs and the attention mask corresponding to each token. Those attention mask will tell me if whether or not a particular token is relevant in order to generate the next token. Now, so once you have the outputs, once you have and before generating the output, actually it's always recommended to set off the gradient computation. So here I'll say with torch.noGrad, generate the outputs here. Right, so that will give me the outputs without computing the gradients in between, and then I can get the attention weights by using the outputs as well, and from outputs you have the attention scores. Right, so within output you have the attentions, and then we'll pass which layer we want the attention from, so that is the layer index, and then within the layer index we'll say which head we want to calculate the attention from. Right, so within each layer you need to get the head index passed, and we'll convert it into a NumPy array. Okay, so here this will return me what the attention weights are for that particular output that we want to calculate. And secondly, we'll also calculate the tokens that are basically generated. Remember that we also want to visualize which tokens gets how much attention. So what I'm going to do is I'm going to use the tokenizer itself to get the tokens back from the tokenizer. So what I can do here is that I can just calculate the tokens above only. So let's get the actual tokens back. So this token can be generated by using the tokenizer as well. And then here we'll say convert IDs to tokens, because in the tokenizer you have a function that can take the input token IDs and convert it back into the actual tokens. So here we have the input IDs from the inputs output that we have received above. So this inputs variable will tell me what the input IDs are. And again, as I told, there is a batch dimension that we have alongside the actual array of inputs. So we are going to squash that batch dimension here to get the tokens back. So these tokens will help me visualize the outputs much better. So over here now, what do we have? So here we have calculated what the outputs are, what the attention weights are, and attention weights are calculated for a given layer and for a given head as well. Alright, so here also we have a batch dimension which we have to squash, and we mention which head attention we are looking at. And once we have these two things, now we can quickly return it back. So I can just return my attention weights and the tokens corresponding to each and every attention. Now once this is done, let's define a few sentences. Let's create a sentence here. So yeah, let's say we take these three sentences only. So the first sentence is I love eating pizza on weekends. The second sentence is my favorite food is pizza, and the third one is I went for a walk in the park yesterday. And then what we want to do is we want to calculate for each and every sentence, when we pass that sentence into our model, how much attention each word gets from the remaining words around the context. Right, so for that what we are doing is we are basically calculating the attention weights and the tokens that are generated, and let's just quickly print out for each and every set of words what is the attention score looking like. And as you can see over here, the output contains quite a lot of information and it is not that easy to visualize, right? So here, in order to see that these are the tokens and these are the attention scores corresponding to each token pair, so visualization like this is not that convenient. So what I am going to do instead is that I am going to use heat maps to visualize this entire matrix in a heat map format. So here I am going to delete this part and let's quickly use matplotlib to actually visualize this particular entity in itself, right? So here firstly what we are going to do is we are going to define a figure, and then we are going to use cborn.heatmap, and the matrix that we want to visualize is attention weights. On x-axis I am going to set the x ticks labels, which are going to be the tokens, and similarly y tick labels will also be my tokens. We'll set a color map to blues because that is the most decent ones. Right? And we'll set annotate to true. So annotation means that now it will go also show me what the outputs are, and the format here will help me decide how much precision I want to show in the attention scores. So this floating point precision is basically going to round off each attention score to 2 decimal places. So right now each attention score is rounded off to a lot more decimal places. I'll just make sure here that it's rounded off to 2 decimal places, and we are going to visualize it as a Seaborn matrix. And after that, once we have visualized it, we can just use plt dot show to basically show what that heat maps looks like, and yeah, it will continue to run in the loop, and that's it, right? So let's run this, and now we'll be able to visualize the attention mechanism in a much more simpler way. So you see here, this is the sentence, I love eating pizza on weekends. So this special token is basically indicating the beginning of a sequence, right? So BOS token. So at the beginning we have this BOS token, and for this BOS token you can see the attention scores that it is getting across the other tokens. If you take a look at the meaningful words, let's say pizza. So when generating the word pizza, it is basically looking the most at the word love. So the attention score between pizza and love is pretty high. Same way if you look at the weekends, so in case of weekends also here it's looking at I, and it is also looking at on, right? So essentially what this particular matrix tells you is how much attention each word is getting with respect to the other words in the context of the current word. Same way for the second sentence, my favorite food is pizza. Here also if you see, for each and every sentence it is basically looking at the corresponding context around it and deciding what should be the most important word when generating the next token. This is the last sentence, I went for a walk in the park yesterday, and same thing here as well. So when you are talking about walk, it is talking about yourself. So here you can see it has the most attention from that particular word. And the second highest attention is going to the word park, yesterday, and the word went. Right? So that's the 3 words that it is paying the highest attention to. And you can go through the remaining matrix in this particular notebook to get a deeper understanding of how this attention matrix is working. So that's all about attention. Next up, we are going to talk about how to train these large language models here, because we have discussed the tokenization, we have discussed embeddings, and we have discussed the building blocks of transformer blocks, which is the attention mechanism. Next up, we are going to dive into the concept of training these models on your own custom datasets. So now let's discuss how exactly is a large language model trained. So in the beginning, we have seen that large language models are a special kind of machine learning models which are trained on huge amounts of data. And these datasets majorly are text datasets, right? And the majority of these large language models, their training objective is to predict the next word in a sequence, right? So depending on the previous context, they want to predict the next word as accurately as possible. So the typical training loop for a large language model is as follows. So the first step is to essentially see the input sentence. So that entire training sentence, the sequence that we want the model to look at, that sequence is fed into the model. The model goes through that input and it tries to predict the next token as accurately as possible. Sometimes it will be correct, sometimes it will be not. So there will be a mismatch between the actual and the predicted value, right? So here it will go through the first input, it will try to predict the next token. But if it is not able to predict, there will be some error there, so which will allow you to calculate the loss. And then you take that loss and you update the parameters of the model which are predicting that token such that it predicts the token as closely as possible. And that updation is done using backpropagation. Right? So these are the 4 major steps, and you continue running this loop for as many epochs, as many iterations as possible. The more iterations you do, the better the model will get at predicting the next token over a period of time. So while training, there is essentially a loss function involved. This loss function that these models use, it tries to reduce the prediction error. Right? So what it tries to optimize is essentially how well the model is able to predict the next token. Right? So it wants you to predict the next token around the context by measuring the prediction error. So how much error the model is making while predicting the next token. Now, and there are multiple ways to optimize this. So if you run this for multiple training epochs, as I mentioned, the model eventually will learn to predict the correct token, right, by correcting its own mistakes. So whatever mistake it made in a previous iteration, if the updation of the weights has happened correctly, then it will be able to predict the next token more accurately. And this happens over a billion training cycles, right? So these huge models that we take a look at, these models are trained for months and months, right? So it's not like you train a model for 1 or 2 hours and you get models like GPT, Gemini, and no, it's not like that. These models are trained continuously for months and months over hardware that you and I, for our commercial purposes, cannot even dream of purchasing, right? So you need such powerful machines that can keep on feeding this model data again and again over billions of cycles until it gets ready for generation of text in real time. So in this demo next, I am going to give you a glimpse into how you can yourself train these models easily using PyTorch. So let's get into the demo and see how training happens within large language model ecosystem. Alright, so again, as always, we'll begin by importing our libraries first. So let's start by importing PyTorch because that's the most important library we'll be requiring today. Then we are going to import datasets because Hugging Face also has a package called datasets which gives you access to a bunch of popular datasets out there that you can readily use for building or learning around how large language models work. So here I am going to use datasets and I am going to use a function called load dataset that will allow me to load any given dataset present inside the datasets package. After that, we are going to import some utilities from our transformers package. Right? So here we are going to import. So here let's say we are going to train GPT-2 model itself, right? So here I want to train GPT-2 model on my own data set. So here I am going to import, let's say, GPT-2 tokenizer, GPT-2 model. Let's also import the trainer class that will allow me to create the trainer for my data set. We'll import training arguments for defining the training arguments at the time of training. And we'll also import a data collator for language modeling. Right, so that these are the important classes that will be required for defining the various aspects of training pipeline. Right, so that's pretty much all. Let's get these imported. And now once the import is done, let's start by basically first creating few directories that are going to be used for storing our results. So remember, when training happens, it's always recommended to save your training datasets intermediately because, as I mentioned, whenever you train, you continue to train over days and months of time. So in between, there are chances that due to some connection issues, due to your laptop malfunctioning or whatever, the training might stop. So in order to avoid restarting your training from scratch, you can create these checkpoints while training your model, and the next time you begin your training, you can start it from the last saved checkpoint also. So this will give you a lot of time, it will save you a huge amount of time which otherwise would be wasted if you had to start your training again. So whenever training any large language model, always remember to cache checkpoints and into a certain directory. So here what I am going to do is I am also going to import the OS package to create some directories internally so that I can actually use it to store some intermediate results. Okay, so here I can use OS to create some directories first. And let's say I'm going to create a directory called results that is going to save the intermediate results here. And I'm going to pass a flag exist OK equals to true. So this exist OK flag is just going to check if this directory is already present or not. If it is not present, it will create it. If it is already there, it will ignore it. Okay. So here, that is basically what this function is going to do. And once this is done, we are ready to loading our data set. So obviously for training, we first need some data set to work with. So over here, I am going to load a data set from Wikipedia, right? So here there is a data set which is available in the dataset module that allows you to load text from Wikipedia. That is what I am going to load here. So here we are going to define our data set, and we are going to use the function of load data set to create or to load data set based on wiki text, right? So over here we need to give what name. So over here you need to give the path and the name of the data set that you want to load, right? So path here is wiki text, and the name of the data that we are loading is wiki text to raw version 1. So this is the data set that I want to load. This data set is nothing but data set available from Wikipedia articles, right? So that is what this data set contains. And if you want, you can train on the whole data set, but that generally is not recommended while you want to just practice it, or you want to validate whether your pipeline is working correctly or not. So the best way to do it is essentially take a small portion of it just to validate whether things are working right or not. And for doing that, I am going to use the split parameter to define that I want to split the training data, and I want to use the first 1% of my entire training data that is available, right? So whatever data is available, whatever the volume is there, so I can actually use the data set here, and I can say that whatever the first 1% of the data set is, just give me that into my data set, right? So here, instead of loading everything, I'm just gonna load the first 1% of all the available data out there. Okay, so let's load this first. Let's check what the length of the data set is. So in this particular demonstration, we are going to be training using 361 text samples. Let's also see one of those text samples to get an idea around what type of data actually we are working with. So I can say data set at the index, so I can pick the first sample, and here there is a text keyword that you have to call. So when you run it, let's take that one. Right. So here you can see this is basically one of the text field that is available. You can keep on iterating here. So here the second one is also blank. Let's pick something else. Yeah, so you can see here this is another text that is available. So this is around I met with positive sales in Japan. Some Wikipedia article around sales in Japan and so on and so forth. So each one of these data set sample contains some data which we are going to work with for training our model. Alright. So that is basically how we have loaded our data set. So data set loading is currently done. So after we have loaded our data, now we want to make sure this data set is ready for training or ready to be fed to a large language model. So next up, we are going to define our tokenizer, because these sentences, like we have practiced till now, they are not converted into a format that these language models can understand. For doing that, we need to define our tokenizers as well. So next step is basically to define our tokenizer and our model that we want to train here. So the first step here is to define the tokenizer. So let's create that. So here we'll say tokenizer. It's basically GPT-2 tokenizer, and the model is essentially the GPT-2 model. So we define our model and our tokenizer, and in this particular demonstration, since the GPT-2 model does not have a default padding token defined, because all of these sentences that are there, these sentences will be of different length. And when training any particular transformer model, you need to ensure all your training samples are of equal length, right? So transformers, when they take an input, they expect the input to be of same length. So over here, we need to first ensure that all the input sentences are padded correctly. And for doing that, we need to make sure that the model has a padding token available. Okay, GPT-2 unfortunately does not have a padding token as such. So what I am going to do here is I am going to set the padding token as the end of sentence token. No, sorry, not model, it's a tokenizer level detail. So since the tokenization is doing the padding, so I am going to use the padding token. I am going to set it at whatever the end of sentence token is for this particular model. It doesn't matter which token we use. For this demonstration, I am using the end of sequence token, but for GPT-2, all of those three are pretty much the same. So here I am setting tokenizer pad token as the end of sentence token, because that will enable my tokenizer to make sure the output sentences are of equal length all across. Okay, so that's basically our model and our tokenizer set. Next up, we are going to set up the devices for training. Now, what devices means? So whenever you train any model, you need to select whether you want to train on CPU or GPU. So if your laptop is basically containing GPU, then you obviously want to use GPU for training, because that is going to speed up your training as well. If you train the same model on a CPU, it will take a lot more longer. So over here we are first going to define the model, or define the device for training our particular large language model. So here let's create the device. This device is going to be an object of torch.device, and here we are going to say that I want to currently train on my CPU. Okay, I'm not going to use the GPU as such. I'm going to train on my CPU. So now what we are doing here is basically we are taking the model that we created previously. This model might not be present on the presented device, so it could be created for a different device. But over here we are ensuring that whatever the model parameters are, those model parameters are created in a way that can enable the training to be performed on my machine's CPU rather than training on some other device. Okay, so that is basically what we are setting up. So we created the model, we created a device for this model to be trained on, which is currently a CPU, and then I transferred my model to be able to run or train on a CPU as well. Okay, so that is basically the setup part. Now we are going to define a function that will tokenize each one of my sentence. So here we are going to create a function tokenize, and this tokenize function is basically going to take in a set of examples that we're supposed to tokenize, right? So over here we need to essentially tokenize our data set, and what we are going to say is essentially it is going to return back a tokenizer object which is tokenizing all the example text. Right? So whatever examples I will give, it will extract the text from these examples. Remember that above here also, in order to get a particular text out, I told it to extract it from the text attribute. So what it is going to do is it's going to take those example, it's going to extract the text from it, right, and then it is going to make sure that truncation and padding, all of those are available, right. So let's set all of these parameters one by one. So here let's first set the truncation. So we'll say truncation as true. So wherever the sentence length is longer than the maximum limit of that large language model, it will truncate it. Okay. After truncation, let's say we define the padding as well. We have already created the padding token above. So here we are defining the padding next. Then we are defining how much is the maximum length of each word that will basically go to our language model. So instead of creating a longer context here, we are going to create it as a shorter only. So I'll say that maximum length is supposed to be 32 only, right? And in this particular case, finally, so over here we are just wanting to say return tensors as none. So what this will do is basically this function will take an input example text, and the output will be created as a list of tensors that we want to train upon, or list of numbers that we can actually use to tokenize our dataset. Let's quickly create a tokenized dataset. So here I'll say tokenized, and we'll take our original dataset which we have defined above. So remember, we already have the dataset created. So this dataset is supposed to be mapped. So here I'll say dataset.map, and here I'll map the tokenized function to this dataset, and let's keep it as a batched format. Right, so what this does is basically it's going to create a batched version of my dataset, and next up I'm going to ask it to remove certain columns from my data. So in this particular case I can say remove columns. So here it is going to remove the text column from my data, and finally let's set a description here as tokenizing dataset. So now this particular portion is done. So what it has done is essentially it has tokenized all the 367 samples for me. So in this particular case, whatever the function was, it applied this function which is returning the tokenizer output from the tokenizer, which is processing all the data here, right. So it takes the example sentence that we provide, and that example sentence it will take the text column, right, and from the text column it is going to truncate and pad it if the maximum length is not provided, and it's going to return me back whatever the tokenized format of that sentence looks like. Right, so let's quickly check the length of the tokenized data as well. So here you can see the length is also the same. So we had 367 samples in our original data set, which is now tokenized by running this function which we have created above. So what we have done until now is basically we have defined our model, we have defined our tokenizer. The data set that we had, that data set is completely tokenized. Now the last step that is supposed to be defined is essentially the training arguments and the training loop. So next up we are going to create that. Before that there is one last step to be done, which is to create a data collator that can just collate the data and provide the PyTorch tensors for our model to be working on. Okay, so in this particular case, we did not create the PyTorch tensors here. Rather, we are defining a data collator which will essentially collate the data, batch it and return the PyTorch tensors for our processing further on. Okay, so here we will create a data collator. It's not mandatory, but it's always recommended to create a data collator because it makes the processing much more easier for us. Right, so the inputs for a data collator, the first thing that we need to pass is the tokenizer that we have created. And then MLM, which is mass language modeling, will set it to false. And finally we'll say return tensors as PyTorch. Right, so this data collator that we are creating, this data collator is going to work on the tokenizer object that we have defined above. Mass language modeling, again I am not cover mass language modeling here, but it's basically a way of training your data set. Here I am not following it because I want to train a much simpler model. And the output tensors will be created as PyTorch tensors. That's why I have defined the output to be created as PyTorch tensors here. So now we are going to create our training arguments. So these arguments will allow me to define how my model is supposed to be trained. So here we are going to create our training arguments. So in these training arguments, there are certain parameters that you are supposed to define. We'll define these parameters one by one. The first parameter that we are going to define is basically the output directory. So this output directory basically is the directory in which all the results are going to be stored. So here we have already defined it above. We have already created a directory here. So that is going to contain all the intermediate results for working. So in this case, I am defining which is the directory which is going to store all of my results. After output directory, then we are going to create, or there's one more parameter that will basically override the output directory. So it means that if your output directory already contains some data, it's going to override the previous data with the latest one. So this means that whatever the data which was present here there, instead of using it, it's just going to overwrite it with the latest data that you are going to feed right now. We'll define some training epochs. So here we'll say the training epochs are 1. We'll just go through the entire data set just once. So we'll do one pass along the data set, and per device eval batch or training batch size. So for each device we'll define the batch size. So the batch size is basically in one pass how many documents are going through the model. So you can set it up to as high as possible or as low as possible. So the smallest one is 1 and the maximum is 367, because if you want to pass the whole data set in one batch, that you can do. So we are going to, let's say, keep a batch size to 8. So in one go it's going to take 8 samples, or 8 might be a bit bigger. Let's use 4 for example. So it means that when it processes or when it does one forward pass, it's going to take 4 sentences together in order to calculate the losses and backpropagate that loss to update the parameters based on the losses for the first 4 sentences in batches. Next up, you can, if you want, you can create warm-up steps, but here let's keep it simple. Let's create some logging steps as well. So let's define a logging directory. So the logging directory is typically used for creating logs. So if you have that, it's well and good. It's always recommended to keep some logs running. We can even define at what interval do you need to log. So let's say logging step is set to 10, which means that it will wait for 10 iterations to complete, then it will append the next log. Right? So when it is logging, it will log the losses, it will log everything pertaining to that current training iteration. Right? And save steps. Next up we have save steps. So save steps is going to basically define how many steps or how many iterations you have to go through before you create one checkpoint. Right? So you can again keep it for a bigger value, or you can keep it at a smaller value. So let's say you define training steps, saving steps to 20, which means that it will wait for 20 steps to complete before creating a checkpoint within your results directory. Okay, so that is what the save checkpoint steps does. Then we have save total limit. So save total limit means that out of all the caching, because here you can see we have 367 samples that we are going, and we will do it in a batch size of 4. So it means like all in all we have like 92 steps that we can go through before completing one complete epoch. So those 92 batches, either you can create checkpoints for all of those 92 steps, but it doesn't make sense. So here you can limit how many total checkpoints you want to keep. So 2 here indicates that it will keep the latest 2 checkpoints every single time. So whatever the previous checkpoints are, it will overwrite it, and 2 latest checkpoints will be preserved. You can increase it if you want to keep more checkpoints, or you can decrease it as well. Okay, and then finally, so here we'll define some parameters which will prevent, I don't want to push my train model to the centralized hub for Hugging Face, so I'm just setting push to hub as false, and logging first step, log level is info, log level will set to info, so it's going to create logs at an info level. And finally we'll define certain limitations on the or certain restrictions on how much gradient can be computed. So max gradient norm means that it is going to perform gradient clipping. So if your gradient computed gets too high, you do not want your gradients to become too high, because that causes a problem in itself. So over here we are setting that, okay, the maximum computed gradient cannot be more than 1. So it will clip the maximum gradient to always 1. We'll set a learning rate here. So let's set it at 5 e raised to power minus 5. So we usually want to keep learning rate pretty small, like you do not want to keep a learning rate too high, otherwise the gradient can explode quite quickly. So we want to keep the learning rate as small as possible, and we'll use the floating point precision as well, that again we are not consuming too much of the memory while training. And finally here we are not going to train this model on CUDA, so that's why I'm just going to say no CUDA as true. So we are not training the model using any complicated I don't have any GPU right now on my system, so therefore I'm not going to train this model on CUDA CPU. So therefore here this CUDA is set to false, and these are the major parameters that you have to define. Some of these parameters can be omitted, but I just wanted to give you an overview of some of the important parameters that you need to know when setting up your training arguments. So once these training arguments have been set, the last step is to basically create the trainer that is going to train using the training arguments. So here we are going to now define our trainer here. So this trainer will first take a particular model. So the first part is to give the model that you want to train. So we have already defined our model to train. After that you need to pass the training arguments. So the training arguments are passed to the args parameter. So these are the training arguments that you want. And finally we'll pass our data collator that will feed all the data for our training, right? So here we'll say data collator is the data set, and finally the training data set is not this one. The data set that we are training on is basically the tokenized data set that we have already created, and that's it, right? So in this particular case we are basically defining the data set, the collator that will feed the data to our model, the arguments for training, and the model that we actually want to train. Right, and yeah, that's it. And the only thing that is left to do is basically start the training of this model. So let's quickly start the training. Okay, so in order to start the training of this model, just need to call the train function, and let's begin the training. Okay, so previously I was getting an error. The reason behind that error was I was using the wrong language model here. So previously we were importing GPT-2 model, which does not support training, right? So it only supports inference. So in this particular case here I have imported the GPT-2 LM model head, which allows me to for language modeling tasks, this model allows me to train or fine tune a language model as well using the GPT-2 architecture. So just change the model here. So I have changed the head here, and again I am using the same pre-trained model for GPT-2 that will allow me to back propagate the losses as well. And then the rest of the stuff remains the same. Here I am going to set the same set of training arguments as the previous one. Right, so here these are the same set of training arguments here. We'll define our trainer, right? So here we have defined the trainer previously, and then we can call the train function to start the training steps. And you will start to see immediately that total number of samples that we are training on are 367. We are training for one epoch. right? And then instantaneous batch size, here we have set the batch size to 4, and here we are setting the number of batch size parallelly is also remaining 4. We'll have total of 92 steps before ending our loop, and these are the total number of trainable parameters. And you will see immediately, intermediately, it will keep on telling you that what's the latest model checkpoint, what's the propagation of the losses. So we do expect the loss to continue to go down. And you can see initially the loss was at 4.83, which has come down to 4.68. And after 90 odd steps, here you can see now it will continue and it will stop the training. Right, so you can now see this model has now been trained, and the latest model is also saved in the checkpoint, and you will be able to use this model and load this model from the checkpoint in order to start your inferencing. That's pretty much how you can easily train any large language model. Next up, we are going to talk about how to use this trained model to start the inferencing, or how to decode by using a trained language model or any other language model for that purpose. Alright. So next up, we are going to understand how to decode from a text generated by these language models. Because up until now, what we have discussed is basically how to train these language models. So in the training phase, you basically take these language models, you have your sentences, these sentences are divided into tokens, and these tokens are then fed into language models, which allow these models to train their parameters better. But once these models have been trained, you can start using them for inferencing. So once a trained model is available, you can start your inferencing by, let's say, passing a token of hi. So what this language model will do is, this language model will take this token, convert it into its input token ID, and then feed it to this model. And then once this model gets this token, it's trying to predict what the next possible token of the sequence should be. So for generating this, remember, each language model has its entire vocabulary. So this vocabulary is basically all the individual tokens that are available to be predicted. And what this language model currently does is basically it's going to create a distribution of probability across all the available vocabulary tokens, right? So each of these tokens will get a probability, right? So whatever the last token probability is, that will be created. And the idea here is to essentially understand how to pick the next word out of these several available tokens. And for choosing the best word out of these collection of tokens, you have different strategies that typically you can choose from. The first strategy, which is typically used in this particular case, is known as greedy sampling. So with greedy sampling, what do you do is that you take the word with the highest probability. It's pretty simple. So whatever the first word is, based on the first word, the model needs to predict the next word. So for that, it's going to generate a probability distribution across all the words in the probability. And greedy selection simply picks up the word with the highest probability. So whichever probability is the highest, choose that as the next token of the sequence. The second one is known as random sampling. So in sampling, what it does, it basically creates or picks up a sample from these generated set of values based on the associated probabilities. So in this case, although the word with the highest probability gets the highest chance of picking, but it's not guaranteed that every time it will be generated. So the model here is generating a probability distribution, but it's not guaranteed that this probability distribution will always give you the same value, because that's what probability means. If you toss a coin and both cases have 50-50 chances of heads and tails, so it doesn't mean that every time you toss it, one time you get heads, the second times you get tails. It is very much possible that due to random chance, first and both the second becomes a head. The same thing goes here as well. So although you have a probability associated, but the highest probability does not mean that every time the same word should be chosen. So what it does, the random sampling, based on the probability, it is going to randomly choose a word. And whichever word has the highest probability has the highest chance of getting selected. But now in this particular random sampling approach, chances are that words that are having a lesser probability can also get selected because they have a non-zero probability of getting selected, which can lead to sentences which are not that meaningful to understand. So therefore, in order to limit that, you can actually use the top k, which essentially first selects the top k value. So k here becomes a hyperparameter that you can fine tune, which in this case, if you say 10, so it's going to first select the top 10 values only based on probability, and then going to randomly sample from those top 10 values itself. It's not going to consider any other set of values. So it's only going to consider those top 10 values to select from. The fourth option is top P. So top P is also known as nucleus sampling. So in this case, P is basically the cumulative probability that you want to assign. So what it means that it basically starts off with the first word. So if first word gets, let's say here you have mentioned that the cumulative probability should be 85%. So what it will do, it will try to create a sample such that the cumulative probability of those sample, the smallest sample possible, that such as the cumulative probability reaches this threshold. So it will first pick the word with the highest probability. Let's say that word gets 15% probability. Then the second highest word gets 11%. Then the third highest gets 10%, and so on and so forth until it is able to cumulatively add up all the probabilities to 85%. And then whatever sample gets generated, then from that sample it will choose the next word randomly. And last but not the least, you have the beam search, which in this particular case, in beam search, what happens is that it essentially selects multiple tokens for the first step. It doesn't just choose one sentence for the first step, but then after choosing one step, it is then again going to beam out and select multiple options from the second step as well. So beam search is a little bit complicated to implement, because here you have to keep a track of multiple options from each step. So at the first level, you can take, let's say, 3 options. And then for each of those 3 options, you again generate multiple options. So that's how you create multiple sentences that you can choose from. And then out of those multiple sentences that you have created, you choose the one that best fits your description. So these are the different strategies that typically people use for decoding outputs from a language model. Apart from that, there are some other parameters that you can even choose from to order or to control how the exact generation is working. And one such parameter is known as temperature. So the analogy behind temperature is that if you set temperature to 0, right? So if you set it to 0, then every time you are going to get the same exact result. So with temperature, you essentially control the randomness in your outputs or the creativity of your outputs. The higher your creativity goes, right? So if you increase the temperature, the model outputs will get more and more wilder. Right? So it will get more and more creative and start giving you responses which are deviating from the previous values. And the lower you keep it, the safer your outputs will be. And generally, when a model has been fine-tuned, when a model has been trained, you generally keep the temperature to 0 so that every time you run a particular input, you get the exact same output. Let me give you some demonstration of these different tuning strategies one by one so that we can see those strategies in action. Okay. So to demonstrate these decoding strategies, let's first import our tokenizer and our model, right? So here again from transformers, I'm going to import models that allow me to create these decoding strategies. Here also we are going to use GPT-2 language model because we are using this model for language modeling purposes, right? So that's the model that we want to use. And the tokenizer is again GPT-2 tokenizer. And we'll also import PyTorch as well. So after importing both of them, we'll now define our model first. So let's create the model, which is the GPT-2 and the tokenizer. Again, the GPT-2 tokenizer, not from pre-trained. Right, so we'll define our model and our tokenizer as always. And let's create a simple sentence that we want to analyze or a prompt that we want to analyze. So let's say here I give it a dummy sentence which says a robot walked into a pizza shop and left, right? So here let's say this is a sentence that I want to generate, right? So this is an input prompt and I want the help from this model to complete this sentence. Right? So this model is basically available and I want to use this model to generate a particular or complete this sentence for me. A robot walked into a pizza shop and that's it. So like the next word is supposed to be given to me by the model. And here we'll see how different decoding strategies are giving me different responses, right? So we'll start off first by, we'll first take this prompt and use the tokenizer to tokenize it, to convert it into input ID. So that is what I will do here. So here we'll return tensors as PyTorch. So that is going to basically encode my entire sentence into PyTorch tensors. So here you can just see the input IDs. That's the only thing I want to see. So these are all the individual input IDs that we want to process. So each sentence has been tokenized and after tokenizing it has been converted into its corresponding token ID. Now what we want to do is we want to actually help or take the help from the model to generate the next word in the token sequence. So for that you can either run it yourself, but in order to make things simple, we are always suggesting to use the generate function here because that is the easiest way to give it a sequence and then ask the model to generate the next token in the sequence. So we'll start with the greedy output first. So here we are going to use the generate function to generate based on the input IDs that we are passing, and over here let's say the maximum length that we want this sentence to be is of 20. Right, so here what we are doing is basically we are asking the model to generate a sequence based on the input IDs that we have created, and to make sure that the maximum length over here is essentially 20. Now over here I am not defining any other parameters because the default implementation is greedy only. Right, so when you want the greedy output, just ask the model to generate text and define what's the maximum length of text that you want to generate. Right, so in this particular case, okay, that's okay. Attention mask is not set. I am okay. Right, so we have to pay attention to all the tokens, so that's completely fine. Right, so now the greedy output is currently a set of tokens only. So here you can see the greedy output that is generated. These greedy outputs are also tokens. So what we have to do now is we have to take these greedy output and decode it. So for decoding, again I will use my tokenizer only. So here I will say tokenizer.decode. So let's say greedy output. Let's just define this, right? We'll just say tokenizer.decode greedy output at 0. Right, so here you can see with the greedy output, this is what the complete sentence looks like. So a robot walked into a pizza shop and asked for a pizza. The robot then asked for a pizza. Right, so in this particular example, you can see this is what the sentence completion is looking like when you are using a GPT-2 model with the greedy output. Right, and in this particular case, how the greedy output is working is that it is taking the current context after and the next probable word which is things is the most likely is asked, and after asked it again picks for, and then picks A and then picks pizza, after which it then starts a new sentence. So here end of sentence token is generated, after which it starts a new sentence. The robot then asked for a pizza. So here you can see these are the tokens that are generated by this particular model. That is the greedy output. After greedy, let's select a top K output. So here again I will say model.generate. Here we will generate based on the input IDs, but this time I will say top K equals to 50, and after saying top K equals to 50, let's say max length equals to, let's keep the max length to 20 only, and let's ask it to do the sampling also. So here from each and every word, it's randomly going to select out of these 50 values, it's randomly going to pick which is the most probable value. Okay, so now here top K output is generated, and then again we are going to use the tokenizer to decode it. So here we'll say tokenizer dot decode top K output at 0. Right, and you can see here this time the answer is different. Here the answer says a robot walked into a pizza shop and took one that had no meat line in it. Right, so in this particular example, although the input is same, but just because we changed the output strategy, instead of picking the most probable token, we selected top 50 most probable outputs and then randomly did a sampling from it. So here we did a random sampling from the top 50 probable tokens to generate the final output. Right, so that is basically the top K output and how you can use it to basically sample using from a top K set of values. Similarly, you can also do it P sampling. So here you can say top P output, and this time we are going to again use model.generate. We are generating using the input IDs, max length set to 20 only, and in this particular case here we are going to define how much is the top P value. So how much should the total probability add up to? So here we are saying whatever are the most probable tokens, the total probability of those tokens should be adding up to 85%. So when the 85% threshold is reached, it will stop putting more tokens in its samples list. And then what we will say is that out of all these, then just do a sampling here. So we will say do sample to true. TH. Right, so now here we now have the top P output, and then after that again we are going to use our tokenizer to just decode it sorry. Oh, and in this case, we'll just pass the value at index 0. Correct. And this time with the top P sampling again, the output is slightly different. Here it says the robot walked into a pizza shop and began asking for orders, then started making them. Right. So here in this case, it's more creative in the way that the robot that walked into a pizza started taking orders and then started making whatever orders the robot has received. So you can see with different strategies, the output are completely different. So in this case, you have to see which strategy works for you best, what set of parameters work for you or your use case the most, right? If you want fixed output, then the temperature has to be set to 0. So over here, you can see right now, doesn't matter how many times I run it, right? So in this particular case, since the random sampling that I am doing, that random sampling changes the way the outputs are selected. So this, again, since in this particular case I am setting the sampling to true, it's going to randomly choose from the set of samples that are available. And in this case, the second time it ran, the output says a robot walked into a pizza shop and began beating the customer itself. The customer had its hands up, right? So again, all of this depends completely upon what parameters the models have been set to. But then again, you can customize these to run as per your choices. And last but not the least, you have the parameter of temperature to also adjust, right? So in this particular case, you can even set the temperature. And here we'll pass the input IDs. Let's set the max length to 20 again. This time we'll change the temperature to, let's say, we can keep a higher value of temperature. Let's use 1.2 for example, and do sample to true. PERATURE. Right, and then once the temp out is generated, let's try to decode it. So here we'll say tokenizer dot decode temp output and index of 0. So in this case, the output is again different, right? So here it's more creative in the way that here it says a robot walked into a pizza shop and was met by a crowd of angry people and they were upset. Right? So this is basically how the different parameters affect how the model is sampling the outputs, and upon changing these, the output itself will start to change. So you have to play around with these different outputs to decode what exact strategy works for your use case the most. Okay, as a rule of thumb, make sure the temperature is set to 0 if you want deterministic outputs. Disable sampling, because if you enable sampling, then again the creativity will come in, wherein for each run the model will give different results. So you do not need to have sampling there, you just need to make sure whatever the output is, it's generated or selected from the desired list of values. Okay, so that's basically all about how to decode a transformer model. So next up, we want to talk about two very important concepts when working with large language models. Now the first concept is of fine tuning, and this concept is coming into picture because of the obvious reasons behind the limitations of training a large language model from scratch. So taking an example, before the creation of these large language models, models used to be pretty small. They could easily fit inside any commercial machines, and you as a user could train your models from scratch pretty easily even on some commercial laptop hardware. But that typically is not possible nowadays. With billions or trillions of parameters to be made available, it's not physically possible for anyone to train a model from scratch. In fact, the demo that we just now did, we actually did not train a model from scratch. We took a pre-trained model and just tuned its parameter to fit the data set that we wanted better. And that technique is basically known as fine tuning, wherein you essentially take a model that has already been trained on billions of data sets, and instead of building that model from scratch, you essentially take that model and feed the information about your domain as well, which makes that model adapted to the knowledge which is present in your data set as well, which previously it lacked. And that exact knowledge is basically parted to the model with the help of fine tuning. Now we have already demonstrated fine tuning previously when we did the training itself. That exact steps are essentially a fine tuning, not a training from scratch. Because in training you would start a model with no parameters or just random parameters and essentially keep on training and training and training until the model generates meaningful responses based on your domain. which can take a lot of resources and a lot of training time, to be very frank. Right? So here the usage of fine tuning comes when you take a model which is trained, let's say, on Wikipedia, which knows what just a regular language means, and then you adapt that model to domains such as medical or programming, etc. Where in medical domains there could be terminology specific to medical which might not be all available on Wikipedia, and hence to make the model more adapted to that domain, you take that model, train it on the data set from your domain, and then make it more knowledgeable about the experiences that you have from the domain that you are working in. Second key important thing to understand from this perspective is of prompt engineering. Now, prompt engineering is the art of designing instructions that can create the outputs which are more business friendly and more precise. Right? Without proper prompt engineering, the model outputs might not be as per your expectations. With the right prompt, you can even get the correct answers from the model which are less expensive. So prompt engineering is just the art of designing the right instructions such that the model starts interacting with you in the way you are expecting in the first place. And there are multiple different techniques with prompt engineering. Right? The first simplest technique is known as zero-shot prompting, in which you basically give the instruction without telling the model how exactly it needs to do it. Right? So in this particular example, let's say the first one is known as instruction prompting, So in instruction prompting, you basically tell the model a certain instruction, and if the model knows what that instruction means, it will try to answer that question based on the meaning of that instruction. So in instruction prompting, you give the model a certain instruction like summarize the text or translate, right, or create a poem. So that is an instruction in itself, wherein you define an instruction and give basically what is supposed to do, right. So after the summarized text, you will pass the text which is supposed to summarize in a given words, which basically that the output that you want to generate. The second one is known as zero-shot prompting. So in zero-shot prompting, what you do is you basically give an instruction and you give a value that is supposed to make the, so in this particular case, you give an instruction and you give what it's supposed to do with that instruction. So in this example here, it says translate hello to French. So in this case, we are not giving it any examples on what the translation of hello looks like in French. The model, we are expecting the model to know that what's the translation of hello is in French. And last is basically a few shot prompting, in which here we say what exactly is the combination of actual and the translated values as well. So in case of few shot prompting, we essentially give an instruction and a few example of how that instruction works in real life. So here you would basically say the instruction translate hello to French with examples like cat has a translation of chat in French. Right? So that is basically the example that you would give, and based on that example, the model will start predicting, you expect the model to start predicting correctly. Right? So let's see it in demo how these different prompting techniques actually work. So for this demonstration, again, we'll begin by importing the libraries first. So let's start by importing Torch. Then we are going to import from transformers. So here we are going to import the models that we are supposed to be using. So let's import GP2 to tokenizer and GP2 to large language model head, right? So both of these will be importing here. Right. So once the imports have been done, let's quickly first create the tokenizer and the model. So here we'll create a tokenizer, right? And we'll create the model as well. And we'll set the padding token in the tokenizer as well, so that later on when it is generating, it knows what the padding token is. Right, so here this sets the padding token as the end of sentence token, which we have seen previously as well. And then we are going to define our device. So the device is basically where exactly the generation is happening. So here we'll say torch.device CPU, and we are going to set the model as well to CPU only. So this will basically make sure the model runs on CPU and not on GPU at the time of generating any text. Alright. So now it's time to define a function that generates text using the model and the tokenizer. So here we are going to define a function that is going to generate text. And this particular model, it's going to take a prompt, that is essentially the instruction that we ask it to generate. And secondly, let's ask how many new tokens we want to generate, right? So here we want to know what are the number of tokens that are supposed to be generated as response. Let's keep a default value of 30 here. We'll set the temperature, which is going to regulate again what is the nature of the creativity of my model. Let's keep the default temperature to 70% and let's say whether we want to do the sampling or not. So are we doing the random sampling at the time of generation or not? So then we are going to define our inputs. So input are created using the tokenizer itself, and the tokenizer will tokenize my prompt and it is going to return the tensors as PyTorch tensors. Right, so here we are defining, or we are actually tokenizing our prompt to create our inputs as well. And once we have that, then we are going to disable the gradients first. And then we are going to calculate my outputs by passing the inputs through the model. Right, so this will basically pass the input token IDs and the attention mask to the model, and the model will then start, or in fact, let's not call the model outputs like this, let's directly call the generate function, because that way we will get the tokens that we are supposed to generate. Right, so in this particular case, let's calculate the output here by calling the generate function directly. Right, and in this generate function we are going to pass the inputs here. So here the first part is to pass the input token IDs. Right, next we also have to pass the attention mask. So here we are going to pass the attention mask as well. The attention mask is also available from our input IDs as well. We say how many maximum new tokens we are supposed to generate, what the temperature is, and what the sampling is supposed to be. Right, so all of these values we have already taken as an input to our function above. Right, so all these are passed to the generate function. Generate function is going to take care of generating the set of new tokens with the temperature and the technique of sampling that we have provided above. Right, secondly, we'll also provide what is the padding token IDs, because the padding is also available here. So we'll basically mention the padding token ID that will allow the model to understand what exactly is the pad token ID, right? So how is it padding the end of sequences, right? And then last but not the least, let's also say how many sequences we want to return. So number of return sequences is 1. So number of return sequences means that at a given point of time, example I already gave of beam search, if you want, a model can generate multiple sentences together. But here we want to restrict the output to one single sentence. So that's why here the output is essentially saying that you keep the output limited to one sentence at a time. You do not want more than one sentences. We just want one single sentence at particular time. So then here we have our outputs ready. Now once we have the output, then what we have to do is we basically need to get the generated text. So let's get the generated text from our output. So here all we need to do is essentially use the outputs to decode, right? And while decoding, I'm going to skip the special tokens. So skipping special tokens means sometimes the model outputs end of sequences, beginning of sentence, end of sentence, right? All of these different special tokens, and I do not want those special tokens to be present in my output. So here I am basically skipping those and I am returning back my generated text. Okay, so here let me just show that later on, not here. So this function is now going to essentially give my generated text to me, and then we are ready to demonstrate the different prompting techniques. So this function is basically going to take my prompt and it is now going to start working with my prompt, right? So here we have defined our function that takes a prompt and based on the prompt starts generating the responses that we want to see. Now next up, let's create some instructions and demonstrate the different prompting technique, right? So let's start with the zero shot prompting technique, right? So wherein we give a simple instructions without giving any particular samples or examples to it, and let's see what the output of the model looks like. Let's define one prompt, right? And let's say translate the following English to French, right? So in this particular case, we'll say you need to translate the following sentence of English to French. So in this case, hello, we'll say how are you, And what the model needs to do now is the model needs to continue generation, wherein now it needs to output the French analogous of this sentence that we are giving. So this instruction is telling the model that you need to pass, or you need to translate English to French. Then we are passing the English sentence that it's supposed to translate into French. So now this is the prompt that we have. Now let's see what the output of this particular sentence looks like. And let's print the result. So in this particular case, in French, I'm not sure if it did pretty well, because you can clearly see the French output also looks pretty much like English only. So that's because the first reason is GPT-2 I don't think has any context of what French language looks like. So I think that is the reason why this particular translation task it's not able to do well. And that's the case you will find with almost all of the small language models. So they might not be good at all the tasks, and that is basically demonstrated here as well. So French might not be the strong suite of this model, and that's why because of that you can clearly see that it's not able to understand what you are trying to say. And here, even though we said you need to translate English to French, it's not able to understand that instruction. Is just continuing generation of tokens one after the other. So next up, let's take an example wherein we are giving a few samples, a few examples of what the model needs to actually perform, what task the model needs to actually do. So let's define a prompt here. We'll divide it into multiple lines, and in this case, let's say in the first line we say complete the following, complete the pattern. Right, so here let's say the first sentence we'll say input. We are creating input output pairs basically. Let's say input is the weather is sunny, and output is it's a beautiful day. Right, then the next input, let's take the movie was terrible, and the output here is that it was a waste of time. So now let's give a model another input, and let's say the input is the food tastes amazing, and let's ask the model to generate an output. Right, so here I'll keep the output blank. Right, so over here I am not generating any output, I am asking the model to generate whatever the output is supposed to be. Okay, let's keep this output open. Right, so this is basically what this is the instruction. These are my samples or examples that the model is supposed to analyze, and based on the analysis it's supposed to essentially take this instruction or take this sentence and continue generating a way that sentence is interpreted. Right, so if the weather is sunny, it's a beautiful day. The movie was terrible, it was a waste of time. Right, so if the food tastes amazing, let's see what the model understand and output for this particular prompt that we are passing it. So in this case, let's again get the second result, and here we are going to pass and we are going to print the results. So in this case it actually understood the pattern, but the thing is that here the model was not able to essentially map it back to the sentence that we are actually getting. So here you can clearly see that here, although the input is the food tastes amazing, but the output is again back to what the previous output was. So in this particular example, the model although got what we are trying to do, wherein we are trying to generate input and output pairs combined, but in this particular instruction at least it's not able to understand that what the input is. It's need to take that input and analyze the output based on that. But I hope you get the idea. So the idea of this particular prompting technique is that you give the model instructions and give some samples that basically follow the pattern that you need to do, and then finally give the input that you need to process and ask the model for the output that you need to get. And if the model is powerful enough, it will be able to analyze the samples and generate the output by looking at the input that you want to see. And this is basically a quick introduction to what is the concept of prompt engineering, wherein you essentially design your prompt, design your instructions in a way that make your model give more reliable and more accurate responses. So next up, we are going to continue and discuss what are some of the limitations of these large language models. Because these models have been trained on massive amounts of data, but that doesn't prevent them from certain drawbacks or certain limitations of these. Let's discuss these limitations in detail one by one. The first biggest limitation of language model is the fact that they are very much susceptible to hallucination. Right. The first biggest limitation is that these language models can easily make up facts or hallucinate. What does it mean? It means that without even giving you a hint about it, does not have any knowledge about it, because the language model has been trained to predict sequences. If it finds something that you haven't done in the past, it will still try to generate responses based on what it knows in its knowledge base. So that actually might not be even correct. Right? That is the first biggest drawback of a language model, which is a language model can easily hallucinate and make up facts. The second drawback is that the language models are not always grounded. Meaning that again, it comes from the same fact that it can easily hallucinate and you do not always know what is the source of those information. Right? So whether or not the information is coming from reliable sources or not, or is it just made up? So these language models do not always remain grounded to a particular point. It can easily hallucinate and give you random facts. The second one is known as biases in LLMs. Because these language models are being trained on data set that are previously generated, and these data set can have inherent biases in them. Right? For example, let's say there's a popular bias out there that let's say men are better at certain jobs as compared to women. And those biases are present in the articles that the models have been trained on. So the models also have incorporated those biases in them. Because of this, when the model generates these responses, those biases gets percolated within those responses as well. Right? So the bias actually comes from the data which the models have been trained on. So in order to prevent biases from happening, first we need to ensure the data set that we are training on, those data sets are free from these biases as well. Third, and the very, very important one is that data leakage and privacy issues often comes with language models. Right? So LLMs, whatever information they have seen on, nobody can stop those models to leak those information to somebody else. So if you have trained your language model on your proprietary data set and somehow it got access to someone else, then that other person can easily request information from that language model which is proprietary to your organization. Right? So in this particular case, you always should remember to never share any confidential information with any language models. There are techniques known as prompt injection, using which people often use these language models to extract meaningful information from the company's databases. Right? And because of that, as I mentioned, LLMs often repeat what they saw. So whatever they have seen, whatever they have been trained on, it's very easy for those language models to replicate that. And I think one of that actual demonstrations happened in our hands-on as well. So in this particular case, when you take a look at the output which was generated, so model has seen previously that the output should be "it's a beautiful day." So it's continued to generating the output as, "it's a waste of time" is the latest one. So you can see here that although the food is good, but still it's basically saying the output as a waste of time, because it's very easy for the model to replicate what it has previously seen. So whatever data it has seen previously, it can very easily take that and start replicating that information again and again. Right? So safety and responsible use of LLM is very, very important, because it can be easily misguided, and you need to build on filters and guide rails to make sure the LLMs are not getting data which it's basically not supposed to see. Right? So let me give you a quick demonstration of how this hallucination can look like. So in order to demonstrate this, we will use the same function that we have written previously, in which we are using a prompt to ask model to generate some responses. And let's see, I ask a model a question which we know has never happened. Right? So let's say I ask the model to generate text for a question: who was the first person who landed on Mars? Now I know personally that nobody has ever landed on that particular, no human being actually has landed on that particular planet. So ideally this particular question should not get any answers. Right? So in this particular case, first model is basically says, "if not me then who?" he asks. So here what it has done, it has basically taken that sentence and just started giving out gibberish values as a response to me, which actually honestly does not make any sense as such. But that is what the key idea here is, right? So if your model does not contain any instructions, or in other words, if your model does not have any filters or any guardrails created, even on questions that do not make any sense, the model will still try to generate some responses, which is basically what is hallucination all about. So now finally, to wrap up, let's also discuss some API providers that already have shared their trained large language models with all of us to use. Now, as I told you previously, training a large language model from scratch is it's not a cup of tea meant for everyone, right? So it's pretty difficult to do that. So people often go to these third-party providers like OpenAI, Vertex, Anthropic, etc., which have trained their language models from scratch on billions of data sets, and then they have provided APIs that you can easily use to basically interact with those models in the backend, right? All these API models are fairly easy to use, right? So they have been hosted for us, right? So these API models are very easy to use. They have been hosted for us to actually interact with them, send the prompts, and there are a proper structure that you can follow in order to interact with it. Now, obviously, there are some limitations that these API providers have kept in place to make sure that people are not doing, overutilizing them or exploiting these endpoints for their general usage. So there you will find often usage limits will be created. So in a particular day, you can only send, let's say, imagine like 100 requests, or in a particular minute, you can only send 10 requests and things like that, right? Plus, the only problem here is that with using APIs, you are not always sure whether or not your data is getting shared. If you are using open source API providers, then you have to be aware about the fact that whatever data you are sending to the model, it is getting used for training the models better, right? So these API providers, if they are having an open source model, right, so where they are not charging anything, then your instructions, your chats and all are getting used for training those models even more, right? And then the second option is that you have some open source models as well, like GPT-2 and all that we have already seen. These open source model which these companies have provided, you can just load them locally on your machines, as we have been doing for all the demonstrations, and then they are free for use, right? So here you do not need to worry about paying for those limitations, paying for those different API subscriptions that we pay for, and it is basically open to for you how much of a hardware you have. So you can create your own hardware, you can run these models locally on those machines and start interacting with those models like you interact with any other large language model. And last but not the least, if you have created any open source models, then you can even search for those models on open source portals like Hugging Face, Streamlit, Gradio, etc. So these portals basically give you access to a whole. So if you want to look at all the models that are hosted on Hugging Face, just go to the Hugging Face website. You will find all the transformer architectures that Hugging Face supports, even sentence transformer architectures that it supports. And you can easily load it on your systems like we have been doing from the beginning. Towards the end, I'll give you a short demo of how one of the OpenAI API looks like, which is hosted to us, which is provided to us by OpenAI itself, which we can easily use to interact with OpenAI models in the backend. So now let's quickly demo how an open source API like OpenAI works and how you can interact with it like you interact with any other large language model. So for doing it, you need two things. The first thing is basically you need the package called OpenAI, which you can easily install using pip. And second is you need to create your own OpenAI API key. So what is this OpenAI API key all about? So in order to understand what this key means, it's basically a way wherein you can access the credentials which are available in your account. So in the free tier, you do not get a lot of benefits, but still you are able to access or practice along with the models which OpenAI has created. So in order to create your API key, what you need to do is basically you need to go to the OpenAI platform, which is platform.openai.com, and there you can go to the API settings, or you can just by default you can come here and Google OpenAI API key. So once you click on it, it will redirect you to the API keys section, wherein you can define your own API key by clicking on the button over here. You define your name for a key, that name can be anything. And once you have created your key, you can just create secret key. Once you click on it, it's going to show you what the key contains. You now have to remember to copy this key, right? So you need to copy this key at the time where it is shown to you, otherwise it will go away and you cannot create it again. You have to delete it and create once more, right? So when this shown, just remember to copy it, right? You can clearly see that you won't be able to view it again, right? So once you have copied it, right? So here I have already created it, so I'm just going to delete it. But the key part here is, once you have copied it, go back to your project, create an environment file like this, which is .env, right? So create a file called .env, and in that file paste your OpenAI API key against this variable. Now I know I'm showing you my API key, but don't worry, by the time this video is out, this particular API key will be deleted and you won't be able to use it for your personal cases. So there you have to create your own account, and with a free account you do get some credits that you can use for practicing with OpenAI. And once you have created your OpenAI API key, this environment variable is actually supposed to be set. So what we need to do next is, essentially we need a package which can load this environment variable in our system. So for doing that, a very simple way of doing it is using a package called .env. So this .env package can also be installed using pip. And here we are going to use a function called load.env that is going to load my .env file. So this load.env, the output is true. It indicates that our environment variable has been loaded correctly, and that environment variable of OpenAI API key is what will be required for us to interact with the OpenAI API that has been hosted to us. Once that is done, once you have done it, then it's fairly easy. All you need to do is you need to use the chat interface from OpenAI. So here you are going to say OpenAI.chat.completions.create. And then you need to say which model we need to use here. So in this particular case, I am using a model called GPT-4o Mini, which is a very powerful model created by OpenAI itself. And then you will pass what messages you want the model to answer. So in this case, you have created a particular message in which we are asking the model to interact with the user, right? So the role that this particular message is from a user, and in this case, we are asking the model a question: what is the capital of France? Right, so this role is basically saying the model what type of interaction we are doing with it. So in this case, the content is what's the capital of France, and this is basically the input that the model will take, and it will try to give me my response back. So over here, I'll get a response object back from this particular interaction. So now this response has been generated, and all I need to do is essentially print what this response looks like. So now here I'm going to get my response. Right, so here within the responses there are multiple choices that you get, but here we are only requesting for one, so we are only going to get one choice, and then we can just get the message out from it .content. And you can see here the output clearly says the capital of France is Paris, and this output has been generated by us by the language model that has been hosted by OpenAI. Again, you can get all the details around how to use OpenAI in the reference documents. I am just giving you a quick introduction of how these APIs are supposed to be used. So you just need the API key that allows you to authenticate with the backend API. Get the model. Here I did not need to host this model locally, or model was already provided to me by OpenAI. All I needed was basically the message that the model is supposed to answer, and the answer will be given to me by the model itself. All the hosting and all those things is handled by OpenAI itself. You do not need to worry about it. So that's it. Thank you very much. And that's the world inside large language models, from tokenization to creating real-world AI applications. If this session has helped you understand how AI truly thinks, do hit like, share, and subscribe to Star Agile to get more insights into AI, technology, and project management. I'll see you in the next video. Till then, keep learning.